Long before these places became ruins, they were the centers of worlds now almost impossible to imagine. Fires once illuminated stone corridors, footsteps crossed enormous courtyards, and monuments rose above landscapes that have since changed beyond recognition. Thousands of years later, only fragments remain. Walls without roofs, roads without destinations, chambers without names, and structures whose original meaning has faded with the people who created them. Yet those fragments are enough to reveal something extraordinary. Beneath every layer of stone and soil lies evidence of ambition, knowledge, and ideas whose full stories may never be recovered. Today, we journey through these surviving pieces of the ancient world, searching for the mysteries still hidden between what history remembers and what time has taken away. In Trier, Western Germany, a modern city stands directly above Augusta Treverorum, once one of the largest and most powerful Roman centers north of the Alps. Beneath its streets survive fragments of an engineered city whose water system still raises a deceptively simple question. How did Roman surveyors control a gradient of only a few centimeters across every 100 meters for more than 10 kilometers? Augusta Treverorum was founded around 16 BCE near the Moselle River and expanded dramatically under Roman rule. Its remains were never discovered in a single excavation because Trier continued to exist above them for nearly 2,000 years. Roman streets, sewers, foundations, baths, pipes, and water channels have instead appeared piece by piece beneath later buildings and during construction work. These fragments reveal that the monuments visible today, including the Porta Nigra and enormous bath complexes, were only the surface of a much larger urban machine. One of its most remarkable components was the Rua Aqueduct, constructed during the Roman imperial period to carry water from the Rua Valley toward Trier. The route extended for roughly 13 kilometers and relied entirely on gravity. Yet estimates of its average gradient are extraordinarily small, around 0.06%. At that rate, the channel descended only about 60 centimeters for every kilometer traveled. Over 100 meters, the difference in elevation was approximately 6 centimeters. Water had to keep moving along this shallow slope while the aqueduct crossed irregular terrain, and the engineers had no laser levels, electronic surveying instruments, satellite positioning, or modern topographic maps. The difficulty was not simply measuring one short section correctly. Surveying errors accumulate. A small mistake repeated over several kilometers could theoretically bring the channel too high relative to its water source, creating a section where gravity could no longer maintain the intended flow. An excessive drop posed a different problem, because faster water could increase erosion, damage hydraulic surfaces, and complicate distribution when the supply reached the city. The builders therefore had to establish a continuous descending path through terrain they could not see from a single observation point, then transfer those measurements into an actual channel while excavation and masonry proceeded. Roman surveyors possessed instruments capable of remarkably sophisticated work. The chorobates, described by Vitruvius, could determine horizontal level using a long beam and plumb lines, with water providing another reference when wind disturbed the chords. The dioptra could measure angles and was capable of more complex surveying operations. These tools demonstrate that precise leveling was possible, but they do not preserve the field procedure followed at Trier. No Roman engineering notebook survives explaining how many survey stations were established along the Rua route, how frequently elevations were checked, how accumulated error was corrected, or how separate construction crews ensured that sections excavated at different locations would eventually meet at compatible heights. That missing procedure becomes more intriguing because much of the aqueduct was underground. Subterranean construction protected the water and reduced exposure to weather, but it also created a surveying problem. Once excavation entered the ground, engineers could not simply observe the entire route ahead. The intended elevation had to be transferred from the surface into trenches and underground sections while preserving the tiny overall fall. Even an error that looked insignificant locally could matter when multiplied across kilometers. The surviving channel therefore represents not one successful measurement but thousands of coordinated decisions made along a landscape whose natural contours constantly changed. The aqueduct itself was engineered to protect those calculations. Its masonry channel was lined with hydraulic material to reduce leakage, while underground placement helped stabilize conditions around the conduit. Maintenance access was equally important because mineral deposits and sediment could gradually reduce capacity. Estimates suggest that the Ruhr system may have been capable of delivering on the order of 25,000 cubic meters of water per day, although its actual flow would have varied with operating conditions. At such a scale, small changes in channel geometry could influence an entire urban supply rather than a single fountain or building. This leads directly to another unresolved part of Augusta Trevororum's hydraulic system. Getting water to Trier was only half of the engineering problem. Once it arrived, it had to be divided among neighborhoods, fountains, private consumers, and enormous public facilities. Archaeology indicates that Roman Trier drew upon multiple water sources and employed wells, aqueducts, wooden and lead pipes, drains and underground sewers, yet the complete distribution network cannot be reconstructed. The principal distribution arrangement, associated with the Ruhr supply, remains uncertain, partly because much of the Roman city lies beneath later Trier. That missing network matters because Augusta Treverorum contained facilities with extraordinary water demands. The Barbara baths occupied roughly 42,000 square meters, making them among the largest Roman bath complexes known. Such a structure required far more than pools filled with water. Cold rooms, warm rooms, and heated bathing spaces had to function alongside furnaces, hypercaust heating, drainage channels, and service corridors. Water entering the complex needed to be delivered, stored, heated, circulated, and removed without interfering with other parts of the city. The imperial baths provide additional evidence of this hidden infrastructure, including subterranean service spaces and water management structures that reveal how much engineering existed beneath the monumental architecture seen from above. The drainage system created the opposite problem. Water delivered by aqueducts eventually had to leave the city, joined by rainfall and wastewater. Roman streets could direct surface runoff toward drains connected with larger underground channels, creating another engineered network beneath the urban grid. Because Trier has been continuously occupied, however, these systems survive unevenly. Some sections can be studied while others disappear beneath streets, houses, and later foundations, leaving archaeologists to infer connections between isolated discoveries. This incomplete archaeological map also makes it difficult to determine how the water system changed as Augusta Treverorum expanded. By the late 3rd and early 4th centuries CE, Trier had become an imperial residence and one of the major political centers of the Western Roman world. Population, palaces, baths, administrative buildings, and elite residences increased the demand placed on infrastructure that had developed over generations. Older channels could be modified, new branches added, and distribution points rebuilt. What appears archaeologically as disconnected pipes or conduits may therefore represent different phases of a constantly evolving hydraulic network rather than a single master plan constructed at one moment. The same buried landscape explains why Augusta Treverorum remains unusually difficult to reconstruct. Unlike an abandoned Roman settlement that can be exposed across large areas, Trier cannot simply be excavated down to its ancient street level. The living city occupies the same ground. Archaeologists often encounter Roman structures only where construction, basements, or limited excavations provide access, meaning that major components may survive only meters away from known remains, but remain inaccessible beneath modern property. The Ruhr Aqueduct captures this problem better than almost any other structure in the city. Its surviving sections prove that Roman engineers could carry water over roughly 13 kilometers using an average gradient measured in only fractions of a percent. Their surveying instruments are known, and the physics of gravity-fed water is understood. What remains missing is the operational knowledge between those two facts, the sequence of measurements, corrections, benchmarks, and construction controls that allowed an exceptionally shallow theoretical slope to become a functioning hydraulic structure in real terrain. Beneath Paris, France, streets, universities, apartments, and monuments conceal Lutetia, a Roman city whose most complicated engineering systems can now be studied only in fragments. Lutetia was never discovered in a single dramatic excavation. Its remains surfaced gradually as Paris repeatedly rebuilt itself. Roman walls, streets, baths, drains, foundations, and underground galleries appeared beneath construction sites, while excavations around the Latin Quarter revealed that the monumental Roman city had occupied the slopes of Montagne Sainte-Geneviève on the left bank. The problem was immediately obvious. Archaeologists were not excavating an abandoned ruin. They were trying to reconstruct a city beneath another city. By the 2nd century CE, Lutetia possessed a forum, theatre, amphitheatre, several bath complexes, and an aqueduct, supplying water from sources south of the city. The aqueduct followed a route of roughly 26 kilometers, considerably longer than the straight-line distance to its source region, because Roman engineers had to negotiate the landscape while preserving gravity-driven flow. Estimates suggest that it may have delivered around 2,000 cubic meters of water each day. That volume alone reveals an urban system operating on a scale difficult to appreciate from the surviving ruins. Water had to reach public baths, fountains, and other installations, while continuously descending through a carefully controlled hydraulic network. Yet much of the final distribution system beneath Lutetia has disappeared, leaving archaeologists able to identify the supply route more easily than the complete network that once divided and controlled its water. The most revealing example of this problem lies beneath the area of the modern Collège de France. Here stood the largest known bath establishment in Roman Lutetia, the Thermes du Collège de France, constructed near the end of the 1st century CE and subsequently modified for centuries. The complex occupied almost 2 hectares, approaching 20,000 square meters. What survives is enough to show that this was not simply a collection of pools. It was a large thermal machine in which water supply, furnaces, heated floors, drainage, circulation routes, and massive masonry structures had to function together. Archaeologists have identified 2 large circular rooms constructed above mixed hypocaust systems, possibly containing stepped bathing pools. In a Roman hypocaust, the finished floor was raised above a lower chamber by numerous small masonry supports. Hot gases generated by furnaces moved through this concealed space, heating the floor above before being directed through other channels. At a small scale, the principle is straightforward. At the scale of the Collège de France baths, however, the surviving evidence becomes far harder to interpret. French archaeological research specifically notes the difficulty of reconstructing the technical circuits of the establishment. Some rooms cannot even be assigned a definite function. Parts of the heating network have vanished, connections between surviving sections are incomplete, and much of the structure remains inaccessible beneath the dense fabric of Paris. Consequently, archaeologists understand Roman hypocaust technology while still lacking the equivalent of the engineering diagram for this particular building. That missing diagram matters because nearly 20,000 square meters of architecture could not have been heated or supplied randomly. Furnaces required fuel and airflow. Hot gases had to travel through underfloor spaces without losing useful heat too quickly. Pools needed water at different temperatures. Used water had to leave the building through drainage channels without interfering with incoming supplies. Different rooms were deliberately maintained at different thermal conditions, while bathers moved through a controlled sequence of spaces. Somewhere inside the original structure, all of these systems intersected. The surviving baths of Cluny, another major Lutetian complex, demonstrate just how sophisticated those connections could become. In heated areas, furnaces supplied hypocaust chambers beneath raised floors, while hollow ceramic elements known as tubuli allowed heat to circulate vertically through walls. One furnace still preserves small steps descending toward the boiler area. This meant the building was being heated in more than one dimension, from below through the floors and vertically through parts of the walls, while hot water was simultaneously required for bathing. Yet heating a bath was only half the engineering problem. The system also needed to control where heat did not go. The great frigidarium of the Cluny baths survives beneath Paris, with a vaulted ceiling rising roughly 14.5 meters. The cold room was separated from heated sectors by courtyards and substantial masonry. Seen together, these features suggest that the architecture itself participated in thermal management. Walls, open spaces, heated cavities, and the orientation of rooms helped create distinct environments inside one enormous public building. This makes the missing technical layout of the Collège de France baths particularly frustrating. If Cluny demonstrates what survived, the larger complex shows how much has been lost. Archaeologists can identify individual pieces of the machine, but not always the complete sequence linking furnace to hypocaust, hypocaust to wall heating, aqueduct to reservoir, reservoir to pool, and pool to drain. Paris occupies the missing sections, making complete excavation impossible without removing the city above them. The water entering these buildings introduces another unresolved layer. The main Lutetian aqueduct gathered water from several source areas south of Paris before directing it toward the city by gravity. Maintaining flow over approximately 26 kilometers required careful surveying because an aqueduct could not simply descend steeply whenever the terrain allowed it. Too little gradient could slow the water and encourage sedimentation. Excessive gradients could create damaging flow conditions and complicate distribution. Roman surveyors possessed instruments and established techniques capable of constructing such systems, but the precise organization of Lutetia's terminal distribution network is no longer preserved. Once the water entered the urban area, it had to be divided among installations at different positions and elevations. Reservoirs, channels, pipes and valves could regulate Roman water networks, but Lutetia has not preserved a complete chain from source to every consumer. The estimated daily supply of around 2 million liters therefore raises a deceptively simple question: where did all of it go? The monumental baths must have consumed a substantial share, yet the exact hierarchy connecting the aqueduct with individual public buildings remains incomplete. The same pattern extends beyond water and heating. Lutetia's Roman center was organized around a regular street system on the left bank, with monumental architecture carefully fitted onto Montagne Sainte-Geneviève. Its forum incorporated an underground cryptoporticus, supporting parts of the architectural complex above. Streets, foundations, galleries, and drainage had to accommodate a sloping landscape while creating the ordered appearance expected of a Roman administrative center. Today, however, these systems survive as separated archaeological windows rather than one exposed urban plan. Even the relationship between this engineered Roman city and the settlement that preceded it remains uncertain. Julius Caesar described Lutetia of the Parisii in connection with an island in the Seine, traditionally encouraging its identification with the Ile de la Cité. Yet archaeological evidence has complicated that interpretation, and the precise location and extent of the pre-Roman Gallic settlement remain debated. The Roman city on the left bank is comparatively visible in the archaeological record. The Lutetia that existed before Roman monumental construction is much harder to locate. That uncertainty continues beneath the center of Paris itself. Archaeological work on the Ile de la Cité has revealed Roman remains below later medieval and modern layers, including roads and evidence associated with baths, river installations, and late Roman defenses. Each excavation exposes only a narrow section before the modern city closes around it again. The result is an unusual archaeological problem. Lutetia has not disappeared because its builders left no evidence, but because nearly 2,000 years of occupation have placed that evidence beneath one of Europe's densest historic capitals. In Amasya, northern Turkey, the modern city occupies ancient Amasya, while the cliffs of Mount Harshena still preserve the monumental tombs of the kings of Pontus. Houses, roads, later fortifications, and centuries of rebuilding now surround an ancient landscape whose full engineering plan has never been completely reconstructed. Amasya was never discovered in the conventional sense because it was never entirely lost. Ancient writers, especially Strabo, who was born there around the 1st century BCE, described the city and its royal stronghold, while the enormous openings cut into the cliffs remained visible above the Yeşilırmak River for centuries. Archaeological investigation gradually revealed that these facades were only the most conspicuous remains of a much more complicated environment of rock-cut chambers, passages, stairways, cisterns, defensive works, and water installations extending through Mount Harshena. The most extraordinary engineering problem is immediately visible from the streets below. Beginning in the early 3rd century BCE, when Amasya served as the first capital of the Kingdom of Pontus, royal builders carved enormous tombs directly into the steep limestone cliffs. 21 rock tombs are known in the wider valley, while the principal royal necropolis contains 5 monumental tombs associated with the early Mithridatic kings. Some of these facades rise roughly 8 to 15 meters, dimensions comparable to multi-story buildings. Yet they were not assembled from blocks. The architecture was created by removing the mountain around it. That distinction makes the construction problem far more complicated than simply excavating a cave. Workers had to approach an exposed cliff, establish a working surface, mark the intended geometry, and remove large quantities of bedrock, while preserving precisely the stone that would become the facade, chamber, roof, and surrounding architectural elements. A serious mistake could not be corrected by replacing a block. If a major fracture crossed the chamber, or too much stone was removed from a structural section, part of the monument could be permanently compromised. The surviving tombs therefore represent not only stone cutting but controlled subtraction on a monumental scale. Iron tools, hammers, picks, wedges, scaffolding, and organized labor provide plausible means of construction, so nothing here requires an unknown technology. What remains uncertain is the actual engineering sequence. No surviving Pontic construction manual explains whether workers began at the facade and moved inward, opened the upper sections first and worked downward, or created access platforms before cutting the monument itself. The cliff is steep enough that large working parties would have required secure platforms for both workers and debris removal. Thousands of impacts from iron tools would also have produced enormous quantities of broken limestone that had to be moved away without obstructing the work below. Yet direct evidence for the temporary infrastructure that made this possible has largely disappeared. The precision becomes more puzzling when the interiors are considered. Several tombs were not merely hollowed into the mountain. Their builders cut passages around the burial chambers, partially separating the central mass from the surrounding bedrock and making it resemble a freestanding stone structure enclosed within the cliff. This required excavation on multiple sides of the same mass, while maintaining enough rock to prevent unwanted cracking or collapse. The builders effectively had to visualize the final three-dimensional form before much of it existed, because every removed section reduced their ability to change the design. Why they went to such trouble is still debated. The surrounding corridors may have served ceremonial movement, drainage, architectural display, or some combination of functions. By isolating portions of the burial structure from the mountain, builders may also have reduced direct contact with moisture moving through the rock, although proving that this was an intentional engineering strategy is difficult. The surviving monuments do not provide a written explanation, leaving archaeologists to infer purpose from tool marks, spatial relationships, weathering, and comparisons with other rock-cut traditions in Anatolia. The question of water makes the mountain even more complicated. Mount Harshena was not simply a royal cemetery. Archaeological and historical remains indicate that it also contained cisterns, reservoirs, stairways, and underground passages associated with the fortified settlement above. One rock-cut access structure within the castle descends through approximately 150 steps, while other passages penetrate deeply into the mountain. Their chronology is difficult to untangle, because the same strategic hill was occupied and modified under Pontic, Roman, Byzantine, Seljuk, and Ottoman control. A passage that appears to belong to one system may have been enlarged, redirected, or reused centuries later. This creates a problem beneath the surviving cityscape. The visible royal facades can be dated and studied comparatively, but the complete relationship between the necropolis, fortress, underground water installations, and ancient settlement remains harder to reconstruct. Near the royal tombs, an opening has traditionally been interpreted as the beginning of a tunnel descending toward the Yeşilırmak. Its complete original route and function are uncertain. If it belonged to a water system, it may have helped connect the elevated stronghold with a dependable supply below. If it served movement or defense, the engineering logic would have been different. Without an intact route and secure archaeological context, the mountain does not provide an easy answer. The wider landscape shows that Amasea's engineers were capable of sophisticated hydraulic construction. The so-called Ferhat water channel, generally associated with the late Hellenistic or early Roman period, used rock-cut channels, tunnels, and constructed sections to carry water through difficult terrain. Around 2 kilometers remain particularly visible today, although estimates for the original network vary considerably. Such a gravity-fed system depended on controlling elevation over long distances. Too steep a descent could accelerate flow and erosion, while insufficient gradient could allow sedimentation or prevent reliable delivery. Ancient surveyors therefore had to translate differences in elevation across an irregular mountain landscape into a continuous working route. Greek and Roman engineers possessed surveying methods capable of such work, including leveling instruments and sighting techniques, but no surviving record identifies exactly how the Amasea system was surveyed or who designed its earliest sections. That uncertainty matters because the city developed through several political periods. Distinguishing a Pontic installation from a later Roman modification can be difficult when later engineers reused the same channels, reservoirs, and advantageous geological routes. The tombs preserve a similar historical ambiguity. Their architecture changed during the development of the Pontic dynasty. Earlier examples contain stronger elements associated with Hellenistic architectural traditions, while later monuments developed increasingly distinctive regional characteristics. This suggests that the necropolis was not produced from one standardized plan, but evolved as successive rulers changed how royal authority was represented in stone. Yet the builders repeatedly returned to the same demanding technique, cutting architecture from the mountain rather than constructing it in front of the mountain. That choice is what makes Amasya so unusual beneath the fabric of Amasya today. The mystery is not whether ancient craftsmen possessed tools capable of cutting limestone. Archaeological evidence makes clear that they did. The unanswered question is how those tools were transformed into a controlled construction system capable of producing monumental chambers high on a cliff, while managing access, measurement, fractured rock, drainage, debris, and worker safety. The permanent monuments survive, but almost everything temporary that made their construction possible — scaffolds, lifting arrangements, work platforms, surveying marks, organizational records, and construction plans — has vanished. In Jerusalem, Israel, beneath streets walked by thousands every day, lies the fragmented remains of a Roman city founded nearly 1,900 years ago. Its name was Aelia Capitolina, and although parts of its streets and buildings have been exposed, much of its original plan remains inaccessible beneath the continuously inhabited Old City. The city emerged after Rome's destruction of Jerusalem in 70 CE. During the reign of Emperor Hadrian, probably around 130 CE, Jerusalem was refounded as the Roman colony Aelia Capitolina. Archaeologists did not uncover it in a single excavation. Instead, its structure has gradually appeared through scattered trenches beneath streets, plazas, buildings, and underground spaces, forcing researchers to reconstruct the Roman city from disconnected sections separated by the modern city above. What has emerged is evidence that Hadrian's planners reorganized Jerusalem on a distinctly Roman scale. Excavations have revealed paved streets, column bases, drainage channels, monumental gates, and major north-south routes. Near the Western Wall Plaza, excavations conducted between 2005 and 2010 over an area of roughly 1,500 square meters exposed part of an Eastern Roman cardo about 100 meters west of the Temple Mount. Farther north, remains beneath and around Damascus Gate preserve elements of a Roman entrance complex associated with the city's 2nd century rebuilding. Yet these discoveries expose only narrow windows into Aelia Capitolina, because unlike Pompeii or abandoned Roman settlements, Jerusalem cannot simply be stripped down to its ancient level. This makes the basic shape of Aelia Capitolina surprisingly uncertain. Archaeologists can trace important streets, but they cannot excavate continuously between them. The eastern cardo appears to have followed a route close to today's El Wad Street, while another major north-south axis crossed the western side of the old city. Some streets visible today may therefore preserve an urban logic established almost 2 millennia ago. At the same time, separating Hadrian's original plan from later Byzantine reconstruction remains difficult. A colonnaded street exposed in one excavation may belong to the 2nd century colony, while another section, on apparently the same axis, may have been widened or monumentalized centuries later. The Roman city is present, but it survives as a broken map whose missing pieces remain beneath active neighborhoods. The greatest missing piece is also the most important building implied by the city's name. Aelia came from Hadrian's family name, Aelius, while Capitolina connected the colony to Rome's Capitoline religious tradition. A Roman colony bearing that name would be expected to possess a major sanctuary associated with Jupiter Capitolinus, and potentially the Capitoline triad of Jupiter, Juno, and Minerva. Yet, archaeologists still cannot point to an excavated structure and say with certainty that this was the Capitolium of Aelia Capitolina. One possibility places the sanctuary on or near the Temple Mount. The strongest ancient testimony comes from the 3rd century historian Cassius Dio, who wrote that Hadrian founded a city called Aelia Capitolina on the site of Jerusalem and erected a temple to Jupiter where the Jewish temple had stood. If interpreted literally, this places one of the defining monuments of Roman Jerusalem on the city's most politically and religiously sensitive elevated platform. Such a location would also make symbolic sense. Rome frequently used monumental architecture to express imperial authority, and the Temple Mount already dominated Jerusalem's landscape. Replacing the sacred center of the defeated city with a sanctuary connected to Jupiter would have been an exceptionally powerful statement. The archaeological problem is that direct confirmation is extraordinarily difficult. The Temple Mount has undergone repeated architectural transformation, and large-scale archaeological excavation capable of exposing a complete 2nd century Roman building sequence is not possible there. Later construction altered the platform again, leaving researchers dependent on ancient texts, architectural fragments, surrounding excavations and comparisons with Roman colonial planning elsewhere. The place where the clearest answer might survive is therefore also one of the least accessible archaeological locations in Jerusalem. But there is another possibility. Some scholars have argued that the Capitolium may instead have stood farther west, around the area occupied today by the Church of the Holy Sepulchre. Before Constantine's 4th century church was constructed there, ancient sources describe a Roman pagan sanctuary occupying the area, traditionally associated with Aphrodite or Venus. Roman period remains beneath and around the church confirms substantial activity, but identifying the exact character of the Hadrianic complex is far more difficult. If the principal Capitoline sanctuary stood here rather than on the Temple Mount, the religious geography of Aelia Capitolina would have been fundamentally different from the reconstruction suggested by a straightforward reading of Cassius Dio. That disagreement creates an unusual archaeological paradox. Two of the most significant religious locations in Jerusalem today stand above areas potentially connected with the lost sacred architecture of Aelia Capitolina, yet both have been transformed so extensively that the decisive evidence may be buried, dismantled, or incorporated into later structures. Even the surviving Roman architectural fragments cannot automatically identify the god worshipped in a particular building. A column, foundation wall, or pavement can establish that monumental construction existed, but it cannot by itself reveal whether the complex belonged to Jupiter, Venus, or another cult. The most important temple of the Roman colony may therefore have survived beneath Jerusalem while losing the evidence needed to identify it. The uncertainty extends beyond religion. Archaeological work has also raised questions about the chronology of the city's foundation. Hadrian visited the region around 130 CE, while the Bar Kokhba revolt erupted in 132 CE and continued until 135 CE. For decades, scholars debated whether Aelia Capitolina was established as a consequence of the revolt, or whether the decision to transform Jerusalem into a Roman colony came first and helped provoke it. Increasing archaeological evidence favors substantial Hadrianic activity before the uprising. Researchers have even identified evidence interpreted as construction that stopped during the early development of the colony, raising the possibility that the revolt interrupted work already underway. If that interpretation is correct, buried construction phases beneath Jerusalem preserve something historical texts cannot show directly. A city caught in the middle of being rebuilt when a major rebellion began. Yet even here the evidence is incomplete, because later generations repeatedly cut through Roman deposits, reused stone, and rebuilt on the same ground. The archaeological record does not preserve one clean destruction horizon followed by an untouched city. It preserves almost 2,000 years of structures continually replacing, absorbing, and obscuring one another. That process explains why Aelia Capitolina remains so difficult to understand, despite lying beneath one of the world's most intensively studied cities. Below medieval and Islamic structures are Byzantine remains. Below them appear Roman streets and buildings. Beneath the Roman colony are deposits belonging to Jerusalem before 70 CE, including Second Temple and still earlier Iron Age occupation. Excavating downward can therefore mean passing through several completely different versions of the same city within only a limited area, while adjacent buildings prevent archaeologists from following those layers horizontally. Aelia Capitolina is consequently not a lost city waiting to be uncovered beyond Jerusalem. It is embedded inside Jerusalem itself. Its roads survive beneath later roads, its monumental architecture beneath sacred buildings, and its missing Capitolium may remain beneath ground that archaeology cannot comprehensively open. Each excavation reveals another fragment, but the fragments also demonstrate how much remains unreachable. Nearly 19 centuries after Hadrian refounded Jerusalem as a Roman colony, researchers can reconstruct parts of its street network and trace the outlines of its transformation. Yet the location of the monument that may have defined its very name remains unresolved beneath the living city above it. In Constanța, Romania, a modern Black Sea city stands directly above ancient Tomis, a Greek colony that became an important Roman port. Beneath streets, apartment blocks, public squares, and harbour infrastructure, substantial parts of the ancient city remain inaccessible, leaving archaeologists to reconstruct Tomis from fragments exposed whenever construction opens another window into the ground. One of the most important of those windows appeared in 1959, during construction near Ovidiu Square. Excavation revealed the remains of an enormous Roman complex descending toward the ancient waterfront. What emerged was not simply another buried building, but part of a terraced commercial district dominated by what is now called the Roman edifice with mosaic, a structure generally dated to late antiquity and positioned between the upper city and the harbour below. The scale of the complex immediately raised questions about how this section of Tomis had been engineered. The Roman city occupied a peninsula whose ground descended toward the sea, yet builders created monumental terraces across this changing elevation. Vaulted rooms and warehouses occupied lower levels, while large halls stood above them. The architecture therefore had to carry considerable loads while also interacting with soil pressure, drainage, and a coastal environment. Only fragments of the wider system are accessible today, making it difficult to determine exactly how far the terraces extended or how the engineers controlled water moving through the slope. The surviving structure may represent only one section of a much larger architectural transition between Tomis and its port. Yet the most extraordinary clue lies on the upper terrace. Here, archaeologists uncovered the remains of a monumental mosaic floor whose original area has been estimated at roughly 2,000 square meters. Only part survives, but even that surviving portion reveals a dense arrangement of geometric borders, interlocking patterns, vegetal forms, and repeated motifs assembled from enormous numbers of small stone tesserae. The mystery is not whether Roman craftsmen were capable of producing sophisticated mosaics. Examples throughout the empire prove that they were. The more difficult question is how a floor of this scale was planned, measured, divided among workers, and executed without the design gradually drifting out of alignment. A mosaic, covering around 2,000 square meters, could not simply be improvised from one corner to another. Before the visible stones were installed, workers had to construct a stable substrate capable of supporting the finished surface. Roman mosaic floors commonly relied on successive prepared layers, with coarse material below and progressively finer bedding closer to the tesserae. Errors in the underlying levels could propagate upward, while uneven settlement could fracture the design later. At Tomis, this problem was magnified because the floor belonged to a monumental complex built on engineered terraces overlooking the harbour rather than on an uncomplicated natural plain. Then came the geometry itself. Repeated patterns seem simple when viewed from a distance, but repetition across a monumental surface creates a severe surveying problem. A small angular error, introduced early in a long border, can become a visible displacement many meters later. Parallel lines must remain parallel, repeating units must retain their proportions, and neighboring decorative fields must eventually meet where the original layout intended. Modern builders can establish such geometry using precision surveying instruments and permanent drawings. At Tomis, archaeologists possess the finished fragments, but not the working plans that produced them. The builders certainly had practical measuring technology. Roman surveyors used instruments such as the groma for establishing alignments and right angles, measuring rods for standardized distances, chords for straight lines, and leveling devices for controlling elevation. Craftsmen could also transfer geometric constructions using compasses, straight edges, grids, and incised guidelines. None of this requires mysterious technology. What remains uncertain at Tomis is the exact workflow by which those ordinary tools were transformed into a coordinated design covering an extraordinary area. Was the complete mosaic plotted at full scale before tesserae were placed? Or was it divided into modular fields calculated from a master geometric scheme? Were reference axes established through the entire hall, allowing separate teams to work simultaneously, or did one specialized workshop control the design sequentially? The surviving patterns make the question particularly interesting because a project this large almost certainly required organization beyond the work of a single artisan. Different specialists may have prepared foundations, marked geometry, selected stone, cut tesserae, and assembled decorative fields. If several teams worked at once, their sections eventually had to join with sufficient accuracy that discrepancies did not disrupt the visual rhythm. This implies not only skilled craftsmanship, but a system of measurement and quality control, yet almost nothing comparable to a construction manual for the Tomis project survives. Even the materials introduce another layer of organization. Thousands upon thousands of tesserae had to be produced in suitable sizes and colors, sorted, transported to the site, and delivered to workers in a sequence matching the decorative program. The floor was therefore the final visible product of a supply chain extending beyond the mosaic itself. Determining where all of those materials originated and how workshops were organized could reveal whether Tomis depended primarily on local craftsmen or participated in wider networks of specialized mosaic production operating around the Roman world. The lost portions make reconstruction harder. Modern Constanza covers much of ancient Tomis, while later construction, rebuilding, erosion, and changes around the waterfront have altered the archaeological landscape. Researchers therefore cannot simply expose the entire Roman district and trace every wall to its destination. The mosaic survives as part of an incomplete architectural puzzle. Without the full dimensions of surrounding rooms and terraces, it is difficult to determine how the decorative plan related to the geometry of the entire complex, or whether the same proportional system continued into areas that are now destroyed or buried. That uncertainty connects the mosaic to a much larger problem. The Roman edifice with mosaic was not isolated from the city. Its terraces descended toward a harbour that supported the commercial life of Tomis, and lower vaulted spaces were associated with the storage and movement of goods. Amphorae and other archaeological material testify to connections across the Black Sea and Mediterranean worlds. Above these commercial spaces stood monumental architecture, decorated on a scale appropriate to an important urban centre. The result was a vertical arrangement in which trade, storage, movement, architecture, and public display were compressed into the narrow zone between the elevated city and the waterfront. But the ancient harbour itself is incompletely understood. The coastline has changed, and the development of modern Constanza and its port has obscured parts of the ancient waterfront. Archaeologists can identify pieces of the relationship between the Roman city and the sea, yet the complete configuration of quays, warehouses, access routes, terraces, and associated infrastructure cannot be reconstructed with certainty. The mosaic complex may therefore preserve only the upper portion of an engineering system whose lower components disappeared beneath later development. The same problem extends inland. Tomis was occupied and rebuilt through centuries, creating archaeological layers beneath a city that never became an empty excavation field. Streets, buildings, graves, defensive structures, and infrastructure have often been discovered only when modern work penetrated the ancient levels. Recent archaeological investigations in Constanza continue to reveal Roman burials, reinforcing the possibility that substantial sections of the ancient urban and funerary landscape remain beneath areas that cannot currently be excavated on a large scale. This is what makes Tomis different from an ancient city whose plan can be uncovered almost continuously. Here, the modern city controls what archaeologists are allowed to see. A construction trench may expose several meters of Roman architecture and then disappear beneath another building. A burial ground may emerge far from previously known remains. A monumental mosaic can reveal the existence of a complex whose full boundaries remain hidden. Each discovery adds another coordinate, but the complete engineering plan is still missing. In Edirne, northwestern Turkey, the modern city stands directly over Hadrianopolis, a Roman urban centre whose streets, workshops, defences and public buildings survive only in fragments beneath later construction. The buried city became clearer during archaeological work around the Macedonian Tower, one of the most important surviving landmarks in central Edirne. Excavations conducted in 2002 and 2003 exposed Roman remains beneath later occupation, including fortification evidence and, more unexpectedly, a group of pottery kilns belonging to different periods. Instead of revealing a single monument, the excavations opened a narrow window into an industrial landscape that may extend far beyond the excavated area. Hadrianopolis developed from an earlier Thracian settlement and was reorganized under Emperor Hadrian during the 2nd century CE, probably around 123 to 124 CE. Its position was strategically important. Edirne lies within the river system formed by the Tunka, Meric, and Ada, along routes connecting the Balkans with the Bosporus and the interior of Thrace. A city occupying this position required more than defensive walls and monumental architecture. It needed roads, water distribution, drainage, storage, workshops, and an organized supply of manufactured goods. Yet almost none of this infrastructure can now be followed continuously because Roman Hadrianopolis was repeatedly rebuilt during the late Roman, Byzantine, and Ottoman periods, before disappearing beneath the dense fabric of modern Edirne. The pottery discoveries beneath and around the Macedonian Tower make this loss particularly intriguing. Archaeologists identified 4 kilns representing different chronological phases, demonstrating that pottery production repeatedly took place in this part of the city. Material associated with one Roman kiln included 85 recorded ceramic objects, or diagnostically important vessel fragments, 31 of which were complete or nearly complete vessels. These are not isolated scraps accidentally deposited beside a wall. Together with the firing installation itself, they provide direct evidence that ceramics were being manufactured inside Hadrianopolis. A pottery kiln is only the hottest component of a much larger production system. Clay had to be obtained and transported, cleaned of unwanted material, mixed with water, and sometimes tempered before vessels could be shaped. Fresh pottery then required protected space for controlled drying, because uneven moisture could cause vessels to crack during firing. Fuel had to be collected and stored in substantial quantities, while finished products needed areas for sorting and distribution. Waste from unsuccessful firings normally accumulated nearby. Finding several kilns therefore raises a much larger question. Where is the rest of the industrial quarter that supported them? Much of it may still lie beneath Edirne. This possibility becomes more significant because pottery firing required careful thermal control without modern instruments. Roman updraft kilns generally separated the combustion chamber from the pottery load with a perforated floor. Hot gases passed upward through the firing chamber and escaped through openings above. The potter controlled temperature indirectly through fuel input, airflow, kiln geometry, and observation of the firing process. Depending on the ceramic fabric and desired surface treatment, temperatures could commonly rise into the broad range of roughly 700 to 1,000 degrees Celsius. A poorly controlled firing could deform vessels, blacken surfaces unpredictably, or fracture an entire load. Repeated production at the same location, therefore, implies accumulated technical knowledge as well as specialized workers. Yet, the Macedonian Tower discoveries reveal only pieces of that technological system. Archaeologists can study kiln dimensions, ceramic fabrics, and firing traces, but the organization of production remains difficult to reconstruct when surrounding workshops are inaccessible beneath later buildings and streets. It is not yet clear whether the kilns belong to small independent potters, a concentrated craft district, or a larger production network supplying Hadrianopolis and its surrounding territory. Nor is the complete relationship between these installations and the city's changing defensive landscape understood. Their presence close to an area dominated by fortifications today makes the ancient zoning of this part of Hadrianopolis particularly difficult to visualize. That uncertainty matters because Roman industries were not positioned randomly. Kilns generated smoke, heat, ash, and a constant risk of fire, while ceramic production required convenient access to raw materials, water, fuel, and transport routes. Workshops could therefore cluster toward peripheral zones or near roads that allowed bulky goods to move without passing through the most prestigious civic spaces. If the Macedonian Tower kilns belonged to such a district, their location could provide an indirect clue to the organization of streets and neighborhoods that have not yet been excavated. What looks like a handful of furnaces may actually mark the edge of a much larger manufacturing zone buried beneath central Edirne. The ceramics themselves offer another way into the problem. Vessel shapes can reveal what people stored, cooked, transported, and consumed, while microscopic and chemical examination of ceramic fabrics can help distinguish locally produced wares from imports. Mineral inclusions in fired clay can sometimes be compared with geological sources around a city, allowing archaeologists to reconstruct where raw material originated. Firing conditions can also leave mineralogical changes that indicate approximate temperature ranges and atmospheric conditions inside a kiln. In principle, these methods could reveal whether Hadrianopolis maintained standardized production or whether different workshops followed distinct technical traditions. The difficulty is that the excavated sample represents only a tiny portion of a city whose industrial landscape remains largely inaccessible. The same archaeological blindness affects almost every other part of Hadrianopolis. A Roman city of this importance would have required a civic center, religious buildings, public spaces, and a substantial network of streets. Yet the complete Roman street plan beneath Edirne has never been exposed. Ancient coinage associated with Hadrianopolis depicts monumental architecture, providing evidence for an urban environment far more elaborate than the surviving remains suggest. But matching those representations to specific foundations beneath the modern city remains difficult. The Forum and other major civic structures cannot yet be reconstructed with the clarity possible at abandoned Roman sites where archaeologists can excavate uninterrupted hectares. Water creates an equally important missing layer. Hadrianopolis stood within a landscape dominated by major rivers, but proximity to rivers did not eliminate the engineering problems of supplying clean and dependable water to baths, fountains, households, and workshops. Roman urban water systems could combine springs, channels, pipes, reservoirs, wells, and drainage networks, all designed around gravity and local topography. At Hadrianopolis, however, later reconstruction has obscured much of the Roman hydraulic system. Without extensive excavation, it remains difficult to determine how water entered different districts, how industrial activities were supplied, or how wastewater was removed from densely occupied areas. Even the fortifications resist a simple reconstruction. Hadrianopolis remained strategically important long after Hadrian, and its defenses were repaired and modified through late antiquity and the Byzantine era. Walls could be rebuilt over earlier foundations, masonry could be dismantled for reusable stone, and towers could be incorporated into entirely different defensive systems. The Macedonian tower itself belongs to this long sequence of transformation. As a result, surviving masonry is not merely evidence of one Roman building campaign, but part of a complicated architectural palimpsest extending across centuries. This is why the pottery kilns are so valuable. Monumental buildings can disappear through stone robbing and reconstruction, but industrial installations preserve another kind of evidence, traces of everyday technological systems. The furnaces beneath the Macedonian tower show that somewhere below modern Edirne existed spaces where workers prepared clay, controlled airflow and heat, fired hundreds or perhaps thousands of vessels, discarded failures, and distributed successful products into the city. 4 kilns are visible archaeologically, but the workshops, storage spaces, streets, and supply networks that made them useful remain largely unknown. El Sheikh Hamad hides the remains of the ancient city of Dur Katlimu, a settlement that survived extreme heat, floods, earthquakes, and imperial collapse for centuries. Beneath layers of desert soil, archaeologists uncovered strange engineering systems, unusually durable mud brick structures, underground cooling chambers, and administrative records so advanced they resembled a proto-industrial logistics network. Some researchers now believe this forgotten Assyrian city possessed environmental engineering knowledge far beyond what historians once expected from the ancient Near East. The site began attracting major archaeological attention during German-led excavations in the 1970s and 1980s. researchers identified the ruins as ancient Dur-Katlimmu after discovering cuneiform tablets mentioning the city directly. What initially appeared to be another mud brick settlement soon revealed something much more complex. Excavations uncovered massive storage facilities, reinforced riverbank foundations, canal systems, and thousands of administrative tablets dating between the Late Bronze Age and Neo-Assyrian periods, roughly between 1500 BCE and 600 BCE. What shocked archaeologists most was the scale of organization. Dur-Katlimmu was not a small provincial town. At its peak, the city controlled strategic trade moving along the Euphrates corridor connecting Mesopotamia, Anatolia, and the Levant. The number of tablets recovered suggested a bureaucratic system capable of tracking grain, labor, taxation, livestock, and military supplies with astonishing precision. Some scholars compared the complexity of the city's record-keeping to later Persian administrative systems that appeared centuries afterward. The greatest engineering mystery of El-Sheikh Hamad lies in its mud brick architecture. Across the ancient Near East, mud brick was common because stone was scarce and expensive. The problem is that traditional mud brick deteriorates rapidly under environmental stress. Heat expansion, seasonal flooding, groundwater salts, and erosion usually destroy these structures within centuries unless they're constantly repaired. Yet parts of Dur-Katlimmu remain standing after nearly 3,000 years. This becomes even more mysterious when considering the local climate. Summer temperatures in the region regularly exceed 40 degrees Celsius, while winter moisture and occasional Euphrates flooding create severe stress cycles in earthen materials. Under such conditions, ordinary adobe construction should fracture, soften, and collapse relatively quickly. Microscopic analysis of surviving bricks revealed unusual characteristics. Some bricks appear denser than expected, with evidence of partial vitrification on outer layers, a phenomenon normally associated with low-temperature firing. Researchers found traces of clay mixed with fine gravel, organic fibers, ash particles, and mineral-rich sediments from the Euphrates floodplain. These mixtures may have functioned similarly to composite materials, distributing stress and reducing cracking. Some engineers believe the Assyrians may have unintentionally discovered a primitive stabilization process, similar to modern soil engineering. Organic fibers inside the bricks could have acted like micro-reinforcement, while ash additives may have altered moisture absorption rates. Experimental archaeology projects comparing reconstructed Assyrian bricks with standard adobe show that treated mixtures could survive significantly longer exposure to water and temperature fluctuation. The city's walls also reveal evidence of layered construction techniques. Instead of relying on single massive walls, builders often used multiple compacted layers with alternating material density. This resembles later seismic-resistant building principles used in parts of Persia and even Incan retaining systems thousands of kilometers away. The layered design may have reduced stress propagation during earthquakes or riverbank movement. Even more puzzling is the possibility that some exterior surfaces were intentionally heat-hardened after construction. Several wall fragments display mineral transformations suggesting exposure to controlled heating temperatures between approximately 400 and 700 degrees Celsius. If intentional, this would imply large-scale thermal treatment of architecture centuries before similar methods became common elsewhere in the region. No one fully understands how ancient builders developed these techniques without modern chemistry, structural engineering, or industrial kilns. Another major mystery involves the city's hydraulic engineering. Dur-Katlimmu existed beside one of the most unpredictable rivers in the ancient world. The Euphrates could provide fertile agricultural land, but it also brought catastrophic flooding and riverbank erosion. Excavations revealed sophisticated canal networks, drainage pathways, reinforced embankments, and sediment control systems. Some riverbank foundations were constructed with alternating layers of compacted soil, gravel, and organic matter that appear specifically designed to absorb shifting pressure from floodwaters. This engineering approach resembles surprisingly modern geotechnical stabilization techniques. Similar principles are now used in flood control systems to prevent soil liquefaction and structural failure. Yet these ancient systems were built more than 2,500 years before modern hydrology emerged as a scientific discipline. Researchers also discovered evidence that water flow inside the city may have been partially regulated through elevation gradients rather than mechanical pumping. Slight changes in slope directed excess water away from residential districts while preserving underground moisture near storage areas and agricultural zones. Compared to many contemporary settlements that collapsed after repeated flooding, Durkat Limu demonstrated remarkable environmental resilience. Among the most intriguing discoveries were underground storage chambers maintaining temperatures significantly cooler than the surrounding environment. Even during intense summer heat, these subterranean facilities remained relatively stable. Archaeologists identified ventilation shafts and airflow channels positioned to maximize passive cooling through pressure differences and thermal circulation. Modern engineers comparing the structures to later Persian yakhchals and Middle Eastern wind towers found striking similarities in airflow logic. This suggests the inhabitants may have understood fundamental thermodynamic principles through empirical observation alone. Some grain storage rooms were built partially below ground with thick insulated walls and narrow openings minimizing heat transfer. Temperature simulations indicate that these chambers could preserve food supplies far longer than ordinary surface-level storage buildings in the same climate. If accurate, this would mean the people of Durkat Limu developed passive climate control architecture thousands of years before similar cooling concepts became widely documented elsewhere. The cuneiform tablets recovered from El-Sheikh Hamad reveal something equally astonishing. The city operated with extraordinary administrative complexity. Thousands of records documented food distribution, taxation, military movement, labor assignments, livestock inventories, and regional trade. The level of organization required for such management implies a highly efficient communication network connecting warehouses, officials, transport routes, and agricultural zones. Some historians estimate that maintaining this system would have required continuous coordination across hundreds of kilometers along the Euphrates trade corridor. This raises uncomfortable questions about how advanced Assyrian state infrastructure truly was. Traditional depictions often portray ancient empires as administratively primitive compared to later civilizations, but Durkat Limu suggests something closer to a centralized economic control system operating on near-industrial logistical principles. The city may not have possessed advanced machinery, but it clearly possessed advanced systems thinking. The region around the Euphrates has experienced geological activity for thousands of years, yet many parts of Durkat Limu survived for centuries. Excavations uncovered soft foundation layers made of compacted soil, gravel, and organic material beneath several major structures. Modern engineers believe these layers may have functioned like primitive shock absorbers, dispersing vibrations before they reach the upper walls. The principle is surprisingly similar to modern earthquake-resistant engineering. This suggests ancient builders may have developed construction knowledge over generations to help structures survive in an unstable geological environment. Do you think the engineers of Durkat Limu discovered construction techniques far ahead of their time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Hidden deep within the dense jungles of Belize, the cave known as Aktun Tunichil Muknal, often abbreviated as ATM, has become one of the most haunting archaeological sites ever discovered, not only because of its preserved human remains and ritual artifacts, but because of the profound technological questions it raises about how the ancient Maya interacted with one of the most extreme environments imaginable. First systematically explored in 1989 by archaeologist Jaime Ao, the cave revealed an astonishing concentration of ceremonial deposits, over 1,400 catalogued artifacts, including ceramics, stone tools, and at least 14 human skeletons, many of them located hundreds of meters from the entrance. Beyond zones of natural light and deep within chambers accessible only by swimming through cold subterranean rivers, climbing slick limestone formations and navigating total darkness. Yet among all the mysteries contained within ATM, one stands out as both subtle and deeply perplexing. The question of light. How did the Maya illuminate this pitch-black environment so effectively, so consistently, and with so little physical evidence that modern science can barely reconstruct the process? In a cave where even today trained guides require headlamps with outputs exceeding 200 to 300 lumens to move safely, the Maya ventured far deeper with nothing more than organic materials. Archaeological evidence suggests the use of resin-based torches, likely derived from copal, a tree resin widely used in Mesoamerican rituals, but the implications of this are far more complex than they first appear. Experimental archaeology has demonstrated that a typical resin torch burns for approximately 20 to 30 minutes, producing light in the range of 10 to 50 lumens, depending on composition and airflow conditions. In an open environment, this would already be dim. Inside a cave with high humidity, often exceeding 95%, and limited oxygen circulation, maintaining a stable flame becomes exponentially more difficult. Moisture interferes with combustion, oxygen depletion weakens flame intensity, and the absence of airflow prevents smoke from dissipating. Yet, paradoxically, the interior chambers of ATM Cave show surprisingly low levels of soot accumulation on ceilings and walls. This observation has been confirmed through multiple surveys conducted in the 1990s and early 2000s, where carbon residue was found to be present but far less dense than expected if dozens of torches had been used repeatedly over centuries. To understand the scale of this anomaly, it is useful to compare ATM with other cave systems used by ancient cultures. In the famous Paleolithic caves of Lascaux Cave in France, dating back over 17,000 years, extensive soot deposits clearly mark areas where animal fat lamps and torches were used, leaving blackened ceilings that persist to this day. Similarly, in Altamira Cave in Spain, evidence of prolonged illumination is unmistakable, and with thick layers of carbon residue correlating with areas of artistic activity. Even in Mesoamerica, caves such as Naj Tunic in Guatemala display more obvious traces of torch use, including charcoal fragments and burn marks. By contrast, ATM Cave presents a contradiction: clear evidence of repeated human presence deep within, but a relative absence of the environmental scars typically associated with sustained fire use. This raises a critical question: were the Maya using a different kind of lighting technology, one optimized for low smoke output and high efficiency? One hypothesis suggests that the Maya may have refined their torch composition beyond simple resin, potentially combining copal with other plant materials to create a cleaner burning fuel. Ethnographic studies of traditional torch making in Central America indicate that certain hardwood resins, when mixed with fibrous plant matter and wrapped in specific ways, can produce a more stable flame with reduced smoke. However, even under ideal conditions, completely eliminating soot is virtually impossible, especially in enclosed spaces. Another possibility is that the Maya used multiple smaller light sources, rather than a few large torches, distributing illumination in a way that minimized localized smoke buildup. This would require a coordinated system of movement and placement, suggesting not only technical knowledge, but also an organized ritual protocol governing how light was managed within the cave. More speculative, but increasingly discussed, is the idea that the Maya understood and exploited the cave's microenvironment in ways modern researchers are only beginning to appreciate. Subtle air currents, temperature gradients, and variations in chamber geometry could influence how smoke behaves, potentially allowing it to disperse more effectively than expected. Some chambers within ATM show evidence of airflow patterns that are not immediately obvious, possibly created by differences in elevation or hidden passages. If the Maya were aware of these dynamics, they may have deliberately chosen routes and ritual spaces that optimize both visibility and air quality. Such knowledge would not require advanced instruments, but it would demand generations of accumulated observational experience, a form of environmental engineering rooted in intimate familiarity with the cave itself. Even more intriguing is the possibility that light within ATM was not purely functional, but symbolic, and therefore used sparingly and strategically rather than continuously. In many Maya cosmological beliefs, caves were seen as entrances to the underworld, known as Xibalba, a realm associated with darkness, death, and transformation. Within this framework, darkness was not merely an obstacle to overcome, but an essential component of the ritual experience. Light, then, may have been introduced only at specific moments, in controlled bursts, to reveal sacred objects, guide ceremonial actions, or create dramatic visual effects. This would significantly reduce the total amount of soot produced over time, aligning with the archaeological evidence. It also suggests a level of intentionality in light usage that goes beyond basic survival, entering the realm of psychological and spiritual design. The distribution of artifacts within the cave further supports the idea of deliberate lighting strategies. Many of the most significant finds, including the famous Crystal Maiden, a calcified skeleton whose bones sparkle under modern light, are located in areas that would have required precise navigation and targeted illumination. The placement of ceramic vessels, often intentionally broken in situ, appears to follow patterns that are not random but structured, implying that participants could see well enough to perform specific actions in specific locations. This level of precision would be difficult to achieve with unreliable or inconsistent lighting, reinforcing the notion that the Maya had developed a dependable method of illumination, even if its exact nature remains elusive. Excavation records from the Belize Institute of Archaeology indicate that some torch fragments have indeed been recovered, but they are relatively scarce compared to the scale of human activity inferred from the site. This discrepancy suggests either that organic materials decomposed more completely than expected, or that the number of light sources used was lower than modern assumptions would predict. If the latter is true, it implies a remarkable efficiency, an ability to do more with less, to navigate and operate in darkness with minimal reliance on artificial light. Such efficiency could stem from a combination of factors: heightened sensory adaptation, memorized spatial layouts, and perhaps even ritualized movement patterns that reduce the need for constant visibility. In summary, the mystery of light inside Aktuntunishil Muknal is not just about torches or fuel, it reflects how we define technology itself. While modern thinking links technology to machines and visible traces, the Maya may have relied on knowledge of materials, environment, and human perception to create an invisible technology that left almost no physical evidence. The very absence of clear traces at ATM may actually be the clue, pointing to a more subtle and sophisticated form of innovation than we usually recognize. Do you think the Maya truly developed an invisible technology to master complete darkness inside Aktuntunishil Muknal? Or are we simply missing something obvious? Share your thoughts in the comments below. In central Anatolia, nearly 100 kilometers southwest of modern Ankara, a massive artificial hill rises above the dry plains of Turkey. Beneath it lies Gordion, the ancient capital of Phrygia and the legendary city of King Midas. But the real mystery of Gordian is not gold, it is engineering. Hidden under layers of burned cities, collapsed walls, and sealed burial mounds are structures that have survived for almost 3,000 years, with a level of material preservation and architectural stability that still confuses archaeologists today. Although travellers had noticed the enormous mound for centuries, systematic excavation only began in the 1950s under the University of Pennsylvania Museum led by Rodney Young. What archaeologists uncovered was shocking. Gordian was not a single city buried in time. It was a layered megastructure of civilizations stacked on top of one another, with some occupation phases dating back to roughly 2500 BCE. The central citadel mound alone rose over 50 meters high and covered nearly 13 hectares, making it one of the largest artificial settlement mounds in the ancient Near East. The deeper researchers excavated, the stranger the sight became. Entire districts appeared carefully rebuilt after catastrophic destruction events. Massive wooden chambers remained partially intact after nearly 3 millennia underground. Some walls still showed evidence of advanced reinforcement methods. Instead of resembling a primitive Iron Age settlement, Gordian increasingly looked like a city engineered to survive disaster. Most ancient cities expanded naturally over time. Gordian appears different. Archaeologists discovered evidence suggesting the mound itself was deliberately stabilized, using alternating layers of compacted earth, stone debris, clay, and construction fill. These layers likely distributed weight and reduced structural instability across the settlement. This matters because central Anatolia sits within a tectonically active region. Modern engineers use layered soil stabilization techniques to reduce vibration and settlement damage, especially in earthquake-prone areas. Yet evidence from Gordian suggests builders may have understood similar structural principles almost 3,000 years ago. The city's fortification walls also raise questions. Some defensive walls exceeded 8 meters in height and used carefully fitted limestone blocks combined with timber reinforcements embedded within the masonry. Similar hybrid systems later appeared in Greek and Roman seismic construction, but Gordian predates many of those examples by centuries. Researchers found signs that timber was intentionally inserted into walls not simply for support, but to absorb stress and distribute movement. In modern structural engineering, flexible reinforcement is essential for resisting vibration and thermal expansion. Whether the Phrygians understood the physics behind it remains unknown, but the practical result was remarkably effective. The greatest mystery of Gordian lies inside Tumulus MM, a colossal burial mound approximately 53 meters high and over 300 meters in diameter. It is one of the largest burial mounds ever discovered in Anatolia and is widely associated with the family of King Midas, likely his father Gordius. Inside the mound, archaeologists uncovered something almost impossible: an enormous wooden burial chamber still standing after nearly 2,700 years. Wood is one of the least durable ancient building materials. Under normal conditions, moisture, bacteria, fungi, and insects destroy timber rapidly. Yet many beams inside Tumulus MM remained astonishingly well preserved. Some retained tool marks, others still held their structural alignment despite supporting immense pressure from thousands of tons of earth above them. The chamber itself measured roughly 5 by 6 meters and was constructed using massive cedar and juniper beams precisely interlocked without relying heavily on metal fasteners. Some timbers exceeded 25 centimeters in thickness. The engineering precision was extraordinary. Every beam distributed weight in a way that prevented collapse even as the mound compressed over centuries. What confuses researchers is the preservation environment. Scientists believe several factors contributed: low oxygen levels, stable internal humidity, clay sealing layers, and compression from the mound itself. But none fully explain the chamber's condition. Comparable wooden tombs from similar periods across the Near East usually collapsed or decomposed long ago. Even more mysterious is the possibility that the builders intentionally engineered a controlled microclimate inside the mound. Some specialists argue the Phrygians may have understood passive humidity regulation through layered soil density and air restriction. Certain clay mixtures appear to have acted almost like natural insulation barriers. The burial chamber essentially functioned as a sealed preservation capsule. Modern comparisons make the mystery even more striking. Many medieval wooden structures from only 700–900 years ago have deteriorated far worse than the tumulus chamber. Some researchers compare the preservation conditions to the tomb of Xinjui in China, or the frozen Scythian tombs of Siberia, yet Gordian achieved remarkable preservation without ice, chemical embalming or permafrost. The burial feast discovered inside deepened the mystery further. Large bronze cauldrons, iron tools, wooden furniture, woven textiles, and residues of fermented beverages survived in extraordinary condition. Chemical analysis revealed evidence of a mixed alcoholic drink containing barley beer, grape wine, and honey mead. Some researchers recreated the recipe in modern laboratories, showing the Phrygians possessed advanced fermentation practices centuries before many later European brewing traditions. But perhaps the strangest detail is psychological rather than physical. The tomb does not feel improvised. Every structural element suggests planning, testing, and long-term design. Whoever built tumulus understood load distribution, environmental control, timber selection, and burial sealing with a sophistication that feels unexpectedly modern for the Iron Age. At some point around 800 BCE, Gordian suffered a catastrophic fire. Excavations revealed thick destruction layers filled with ash, collapsed roofs, and carbonized debris. Temperatures during the blaze may have exceeded 800 degrees Celsius in some sectors. In most ancient cities, fires of that scale caused permanent decline, but Gordian rapidly rebuilt itself. The reconstruction phase shows evidence of improved urban planning. Streets became more organized, walls were thicker, storage systems expanded. Some buildings incorporated alternating timber and stone construction patterns that reduced cracking during thermal stress and seismic vibration. This is one of the site's biggest mysteries. The rebuilding process suggests the inhabitants learned from disaster and deliberately redesigned the city for resilience. Modern disaster engineering follows similar principles after earthquakes and urban fires. Flexible reinforcement, compartmentalized construction, distributed load-bearing systems, and controlled rebuilding layouts. Gordian appears to have implemented versions of these ideas nearly 3 millennia ago. Another unexplained feature of Gordian involves its storage infrastructure. Archaeologists uncovered large subterranean grain storage pits capable of preserving massive food reserves through harsh seasonal cycles. Central Anatolia experiences extreme environmental variation. Summer temperatures can exceed 35 degrees Celsius, while winters regularly drop below freezing. Yet the storage systems maintained relatively stable internal conditions. Researchers believe the pits exploited thermal inertia underground, minimizing temperature fluctuations naturally. Some also show evidence of carefully designed ventilation pathways that reduced moisture accumulation and prevented mold growth. The scale is equally important. Estimates suggest Gordian stored enough grain to support large populations or military forces for extended periods. This indicates not merely agricultural success, but logistical planning on a state level. Compared to many neighbouring Iron Age settlements, Gordian's storage network appears unusually centralised and technically organised. One of the most fascinating structures at Gordian is the so-called mosaic building. Its floor contains one of the oldest known pebble mosaic surfaces in the ancient world. At first glance, the patterns appear decorative, but detailed measurements revealed extraordinary geometric consistency. Thousands of pebbles were arranged into repeating angular motifs, with highly controlled symmetry across a large surface area. Creating such precision without modern measuring instruments would have been extremely difficult. Minor angular errors compound rapidly over distance, especially in large geometric layouts. Yet the builders maintained remarkable proportional accuracy. Some archaeologists believe this suggests advanced practical geometry knowledge among Phrygian craftsmen. Similar mathematical sophistication later became famous in classical Greek architecture, but Gordion predates many of those achievements. Do you think the engineers of ancient Gordion truly understood advanced construction techniques far beyond their time, or are we still missing part of the story? Share your thoughts in the comments below. Beside the Mediterranean Sea in southern Turkey, the ruins of Soli Pompeiopolis still stand after more than 2,000 years of earthquakes, salt corrosion, coastal storms, and shifting ground. Massive granite columns remain upright. Harbour foundations still survive beneath layers of sediment. Even stranger, some of the ancient mortar exposed to seawater appears stronger today than when it was first poured. Archaeologists expected another ruined Roman port. Instead, they found traces of engineering knowledge that still cannot be fully replicated. The site was first documented by European travellers during the 19th century, but systematic excavations accelerated in the 20th century after large portions of the ancient city were found beneath farmland and coastal sediment. Archaeologists uncovered a monumental colonnaded avenue stretching over 200 meters long, harbour structures buried beneath marine deposits, drainage systems, bath complexes, mosaics, and foundations of sea-facing defensive walls. Geological surveys later revealed something unexpected. Much of ancient Soli had been altered by shoreline movement, sediment accumulation, and possible seismic events. Parts of the original harbour now lie inland, while other sections may still remain underwater. Ground-penetrating radar and sonar scans continue to reveal hidden structures beneath both the soil and the sea. What emerged was not merely a Roman port city, but a technologically sophisticated maritime centre that may have possessed engineering solutions centuries ahead of its time. One of the greatest mysteries surrounding Soli is its harbour system. Ancient Mediterranean ports usually suffered from rapid sediment buildup. Harbours in Egypt, Phoenicia, and parts of the Levant often required constant dredging because coastal currents carried enormous quantities of sand and silt into docking zones. Yet Soli remained operational for centuries. Marine geology studies suggest the harbour may have been designed to manipulate coastal currents rather than resist them directly. Some surviving breakwater stones appear angled in ways that redirect water flow, potentially creating rotational circulation patterns capable of reducing sediment accumulation naturally. Modern coastal engineers have compared this concept to self-flushing harbours, systems designed to use hydrodynamic pressure to clear debris automatically. The strange part is that the mathematics behind these flow control systems were not formally understood until much later in history. Researchers studying Mediterranean sediment transport noted that even small angular changes in barrier placement can dramatically alter erosion patterns. At Soli, several submerged stone alignments appear deliberately positioned according to prevailing current directions rather than simple defensive geometry. If intentional, this would mean Soli's builders understood long-term marine behavior with astonishing precision. Some archaeologists remain cautious, arguing the patterns may be coincidental, but others point out that similar hydraulic awareness appears at Caesarea Maritima, Alexandria, and certain Phoenician ports, though rarely with the same apparent resistance to sediment burial seen at Soli. The deeper excavations go, the more the harbour begins to resemble an ancient maritime laboratory. Among all the mysteries at Soli, none may be more scientifically important than its mortar. Most modern concrete deteriorates rapidly in marine environments. Saltwater penetrates microscopic cracks, corrodes reinforcement materials, weakens internal bonds, and eventually fractures the structure from within. Many modern harbour systems require major repairs within 50 to 100 years, yet portions of Soli's coastal foundations have survived for over 2 millennia. Material analysis performed on Roman marine concrete from Mediterranean sites has shown that ancient builders often mixed lime with volcanic ash containing pozzolanic minerals. When seawater entered the concrete, chemical reactions continued inside the material for centuries, gradually forming rare crystalline structures such as aluminous tobermorite and philipsite. These minerals are extremely resistant to cracking. In modern engineering, this process is astonishing because seawater normally destroys concrete. Ancient Roman marine mortar appears to do the opposite. The saltwater actually strengthens it over time. Some samples associated with coastal ruins near Soli show unusually dense crystalline growth compared to standard Roman concrete. Researchers suspect local mineral compositions from the Cilician coast may have enhanced long-term durability even further. Scientists from modern materials laboratories have attempted to recreate Roman marine concrete using volcanic ash from Italy and experimental seawater curing processes. While some results show impressive durability, no modern recreation has perfectly matched the lifespan of the ancient material. This has created an uncomfortable question for modern engineering. How did ancient builders accidentally produce a marine concrete formula capable of surviving longer than many modern coastal structures? Even more mysterious is the possibility that the process was not accidental at all. Certain ancient construction texts imply Roman engineers carefully selected different volcanic materials, depending on whether structures would face fresh water, humidity, or direct seawater exposure. If true, that suggests a level of empirical chemical knowledge far more advanced than historians once believed. At Soli, the surviving harbour foundations may represent one of the clearest examples of this forgotten material science. And despite satellites, laboratories, and modern computational modelling, humanity still cannot fully reproduce it. The famous Avenue of Soli once held nearly 200 granite columns, many standing 8 to 9 metres tall and weighing several tons each. Granite sources capable of producing stones of this scale do not exist near the site itself, meaning the material had to be transported over enormous distances. Ancient engineers somehow quarried, shaped, transported, unloaded, and erected these columns with remarkable consistency. The logistical challenge alone is staggering. Experimental archaeology suggests moving a single multi-ton granite column using traditional sled systems could require dozens of workers, lubrication techniques, wooden rollers, and carefully synchronized force distribution. Yet Soli imported enough stone to line an entire monumental avenue. Some researchers believe ancient maritime cranes and pulley systems may have been far more advanced than traditionally assumed. Others point to unusual spiral scoring marks found on certain stone surfaces that may indicate rotational lifting or controlled rolling mechanisms. Even more intriguing is the stability of the surviving columns. Southern Anatolia is highly seismic, yet many foundations endured repeated earthquakes. Beneath several column bases, archaeologists identified compacted gravel and layered mortar systems that may have acted as primitive shock absorbers. Comparable seismic engineering has been observed in parts of Peru, Roman Italy, and even certain Hellenistic structures, but Soli remains one of the least discussed examples. The possibility that ancient builders intentionally designed flexible anti-seismic foundations centuries before modern earthquake engineering remains controversial, but increasingly difficult to dismiss. Modern sonar scans suggest parts of ancient Soli Pompeiopolis may still lie beneath the Mediterranean. Researchers have detected geometric formations offshore that resemble harbour walls, foundations, and buried structures hidden under sediment. Some underwater alignments do not match today's coastline, suggesting ancient seismic events or tsunamis may have reshaped the region centuries ago. But some archaeologists believe the visible ruins are only a small part of the original port city. Each new scan reveals more submerged walls, platforms, and linear structures that should not still survive after thousands of years underwater. And the deeper researchers investigate, the bigger the mystery becomes. How much ancient engineering knowledge disappeared beneath the sea with Soli? What do you think is still hidden beneath the waters of Soli? Could an entire ancient harbour city still be waiting to be discovered? Share your thoughts in the comments below. Something about Hoyo Negro does not behave like a simple archaeological site. It behaves like a contradiction preserved in darkness. Hidden deep within the vast submerged labyrinth of the Sacactan system in Mexico's Yucatan Peninsula, this massive vertical sinkhole, dropping more than 30 meters into a chamber of still, mineral-rich water, has become one of the most important and perplexing windows into the earliest human presence in the Americas. First brought to scientific attention in the early 21st century by underwater explorers mapping the cave network, the site gained global recognition after the discovery of a nearly complete human skeleton at its base, later named Naya. Radiocarbon dating and uranium-thorium analysis placed her at approximately 12 to 13,000 years old, making her one of the oldest and most complete human remains ever found in the New World. Yet while Naya's bones reshaped theories of human migration, revealing a striking mismatch between cranial morphology, resembling Southeast Asian populations, and DNA linking her directly to modern Native Americans, it is not the skeleton alone that unsettles researchers. It is the environment in which she was found, and more specifically, the technological implications hidden in the darkness that once surrounded her. To understand the magnitude of the mystery, one must reconstruct the landscape as it existed during the late Pleistocene. At that time, global sea levels were between 100 and 120 meters lower than today, meaning that the entire Sac-Actun system, including Hoyo Negro, was dry, forming an immense network of caves stretching for hundreds of kilometers beneath the jungle. But dry does not mean accessible. Even in its exposed state, the system would have been a maze of narrow passages, sudden vertical drops, unstable limestone surfaces, and absolute darkness beyond a few meters from any entrance. Modern divers equipped with high-intensity LED systems, redundant oxygen supplies, and detailed cave maps still require hours of preparation to reach Hoyo Negro safely. In contrast, a human entering this system over 12,000 years ago would have faced a total absence of natural light, no navigational aids, and terrain that punishes even minor miscalculations. And yet, Naya, or people like her, did enter. This is where the most difficult and least resolved question emerges. How did ancient humans illuminate and navigate such an environment? The assumption that they relied on simple torches immediately encounters a series of problems. In other cave systems around the world, such as Cosca Cave in France, clear archaeological evidence of torch use has been preserved. Charcoal residues, soot deposits on ceilings, and burnt fragments embedded in sediment layers. These traces allow researchers to reconstruct not only the presence of fire, but also its frequency and intensity. At Hoyo Negro, however, such evidence is conspicuously absent, despite extensive surveys conducted by teams from institutions including the Instituto Nacional de Antropología e Historia, INA, and international cave exploration groups throughout the 2000s and the 2010s, no definitive soot layers, no concentrated charcoal deposits, and no clear remains of burnt wood have been documented in the passages leading to the chamber. This absence is not trivial. It challenges the fundamental assumption that fire was the primary lighting technology used in deep cave exploration during the late Ice Age. A standard wooden torch, even under optimal conditions, produces light for perhaps 20 to 40 minutes and emits smoke that accumulates in confined spaces. In narrow cave passages with limited circulation, this smoke would quickly reduce visibility, contaminate breathable air, and leave behind detectable chemical residues. Experimental archaeology has shown that even short-term torch use in enclosed environments produces soot layers measurable in microns on nearby surfaces. Yet in Hoyo Negro, where multiple individuals would presumably need sustained illumination to travel hundreds of meters through darkness, the expected cumulative evidence is missing. One possible explanation is that the traces were erased over time, particularly after the cave flooded during the transition to the Holocene. Water movement, mineral deposition, and microbial activity could theoretically dissolve or obscure soot residues. However, this explanation is incomplete. The same mineral-rich conditions that might remove certain organic traces have also preserved Naya's skeleton in remarkable detail for over 12 millennia, here along with the remains of extinct megafauna such as saber-toothed cats and giant ground sloths. If the environment is capable of preserving delicate bone structures, why would it selectively eliminate all evidence of fire-based lighting? The inconsistency suggests that either the evidence has not yet been found, or that the lighting methods used left far fewer traces than expected. This leads to more speculative, but increasingly discussed hypotheses. Could ancient explorers have used alternative light sources, materials that burn cleaner, produce less smoke, or leave minimal residue? Ethnographic studies of later human groups have documented the use of resin-rich woods, animal fats, and even early forms of oil lamps to produce more stable and controlled illumination. A fat-based lamp, for example, can burn for longer durations with reduced smoke compared to a simple torch, especially if shielded from airflow. Yet even these technologies typically leave behind residues, lipid traces, soot particles, or structural remains of containers. So far, no such artifacts have been conclusively identified in Hoyo Negro's accessible sections. Another possibility challenges our assumptions about human sensory adaptation. Some researchers have proposed that early humans navigating cave systems may have relied less on continuous illumination and more on intermittent light, combined with heightened spatial memory. In this model, small controlled light sources would be used sparingly, preserving fuel while minimizing environmental impact. Movement would occur in stages: illuminate, memorize, advance, and repeat, effectively turning the cave into a sequence of remembered segments rather than a continuously visible path. While plausible in theory, this approach demands an extraordinary level of cognitive mapping ability, especially in a three-dimensional environment filled with vertical shafts and branching corridors. Modern cave explorers, even with training, rely heavily on guidelines and external mapping tools to avoid disorientation. The idea that late Pleistocene humans could achieve similar feats with minimal lighting remains unproven, yet cannot be dismissed outright. Fieldwork conducted during multiple expeditions between 2007 and 2015 further complicates the picture. Divers mapping the Sac-Acton system noted that the routes leading to Hoyo Negro involve not only horizontal navigation but also vertical transitions, including steep inclines and drops that would have been hazardous without clear visibility. The entrance to the sinkhole itself is not immediately obvious. It opens suddenly beneath the cave floor, creating a lethal trap for anyone unaware of its presence. For Naya to have reached this point, whether by accident or intention, she would have needed to traverse a significant portion of the cave system first. This implies repeated access, familiarity with the environment, or guidance from others who had explored it before. None of these scenarios align easily with a model of sporadic, poorly lit exploration. Comparative analysis with other prehistoric cave sites reinforces the anomaly. In European Upper Paleolithic caves such as Lascaux or Chauvet, extensive evidence of human activity is accompanied by equally extensive evidence of lighting technology, torch marks, lamp fragments, and soot layers that map the movement of individuals through space. These sites demonstrate that when humans operated in darkness, they left behind a technological signature. Hoyo Negro, by contrast, presents the inverse, clear evidence of human presence with an almost complete absence of that signature. It is as if the act of illumination itself has been erased from the archaeological record. The implications extend beyond a single site. If the lighting technologies used in Hoyo Negro were fundamentally different, more efficient, less polluting, or based on materials that degrade without trace, then our current models of prehistoric technological capability may be incomplete. Alternatively, if the absence of evidence is due to preservation bias, then Hoyo Negro represents a cautionary example of how easily entire categories of ancient technology can disappear from the record under specific environmental conditions. In either case, the site forces a reconsideration of what we assume about the limits of early human engineering and adaptation. In the end, Hoyo Negro is not just a place where a young woman fell into darkness over 12,000 years ago. It is a place where our understanding of ancient technology itself begins to falter. The deeper researchers look, the more the silence of the cave becomes its most compelling feature, not the absence of answers, but the absence of the very traces we expect to find. And in that silence, one question continues to echo. If ancient humans could move through absolute darkness without leaving behind the evidence of how they did it, what else might they have known that we have yet to rediscover? On a narrow stretch of the Mediterranean coast in southern Turkey, hidden between steep cliffs and crashing salt water, lie the ruins of Eotape, also known today as Atap. At first glance, the city appears small compared to giants like Ephesus or Alexandria, but archaeologists who studied its submerged harbour, fractured sea walls, and cliffside engineering began noticing something strange. Many of its structures survived nearly 2,000 years in one of the most destructive environments possible: earthquakes, sea salt, humidity, and coastal erosion. The deeper researchers examined the site, the more Eotape started to look less like an ordinary Roman port and more like a forgotten experiment in ancient engineering. The ruins were first systematically documented in the 19th and early 20th centuries during surveys of the Cilician coast. Located near modern Gazipaşa, on Turkey's Mediterranean shoreline, the city was built directly against unstable coastal rock formations. Modern geological studies show the region sits near active tectonic fault systems connected to the eastern Mediterranean seismic zone. In other words, Eotape was constructed in a place where large stone structures should have collapsed centuries ago, yet many sections still remain attached to the cliffs, while parts of its harbour continue to exist underwater. One of the greatest mysteries surrounds the ancient harbour itself. Large submerged blocks forming the harbour walls remain partially intact despite nearly 2,000 years of wave impact. Marine archaeologists noticed that some sections of mortar appear unusually resistant to seawater corrosion. This immediately drew comparisons to Roman marine concrete found at Pozzuoli and Caesarea. In Italy, Roman engineers used volcanic ash known as pozzolana, which chemically reacted with seawater to form durable minerals like aluminum tobamorite. These crystals actually strengthened the concrete over time instead of weakening it. But Eotape creates a major problem for that theory. The region lacks the massive volcanic ash deposits found near Naples, yet mineral traces inside some harbour mortar samples suggest similar long-term crystallization reactions may have occurred. This has led researchers to suspect that Engineers at Iotape either imported volcanic materials through Mediterranean trade routes or developed a localized formula using coastal minerals and kiln ash. If true, it would mean advanced marine concrete technology spread much farther across the Roman world than historians once believed. The harbour also reveals another unexplained feature. Some of the giant coastal blocks were positioned with small gaps rather than tightly compressed joints. At first, this looked like poor workmanship, but structural engineers studying earthquake-resistant architecture noticed the spacing may have served a purpose. Tiny, flexible joints can absorb seismic vibration by allowing stone sections to shift slightly instead of cracking under pressure. Similar principles appear in Inca masonry at Machu Picchu and Sacsayhuaman in Peru, where polygonal stones survived repeated earthquakes without modern cement. The comparison becomes even stranger when measurements are examined. In some sections of Iotape's harbour walls, displacement damage appears far lower than expected for structures repeatedly exposed to seismic activity over centuries. Researchers still debate whether this was intentional engineering or simply an accidental consequence of Roman construction methods. Either explanation raises uncomfortable questions about how sophisticated ancient seismic knowledge may actually have been. Water management at Iotape presents another mystery. Fresh water was critical because the city stood directly beside saltwater cliffs. Archaeologists discovered carved channels cut into coastal rock leading from elevated inland zones toward the settlement. What shocked surveyors was the consistency of the channel gradients. In some preserved stretches, the slope varies by only a few millimeters per meter, a level of precision comparable to famous Roman aqueducts like the Pont du Gard in France. Maintaining such accuracy across uneven cliff terrain without laser equipment or modern optics should have been extremely difficult. Roman engineers are believed to have used water leveling systems, plumb lines, and astronomical alignment techniques. But at Iotape, the channels follow dangerous rocky contours where even small errors could disrupt water flow entirely. Some sections appear carved directly into near-vertical stone surfaces, exposed to sea winds and erosion. The engineering challenge resembles systems later seen in Petra, where Nabatean engineers controlled water flow through desert cliffs with astonishing precision. Even more mysterious is how buildings at Iotape were anchored onto unstable slopes. Modern coastal engineering often requires deep, reinforced foundations to stabilize heavy structures near eroding cliffs. Yet many structures at Iotape were built directly onto bedrock with relatively shallow foundations. Geological analysis suggests ancient builders may have intentionally integrated structures into natural rock stress lines rather than fighting against them. Several cliffside buildings also contain unusually flat stone-cut surfaces beneath the foundations. The cuts are remarkably level despite the uneven terrain. Similar precision stone preparation has been identified in Petra, Baalbek, and parts of ancient Egypt. While none of these sites necessarily prove the existence of lost technology, they demonstrate that ancient stoneworking precision was often far more advanced than public imagination assumes. Another unexplained aspect involves moisture control. Coastal humidity and salt should have rapidly destroyed interior floors and wall systems. Yet remnants of layered flooring systems suggest Iotape's builders used multi-level drainage and airflow techniques beneath some structures. Certain bathhouse remains show evidence of subfloor cavities designed to reduce trapped moisture. These systems resemble passive ventilation concepts used in modern humid climate architecture. Researchers comparing Roman bath complexes discovered similarities to Hipparcourse-inspired airflow systems, although adapted to coastal conditions rather than heating. In practical terms, Iotape may have developed hybrid architectural solutions specifically for surviving Mediterranean humidity and salt exposure. This becomes especially surprising considering the city was relatively small compared to major imperial centres. But perhaps the greatest mystery is why parts of the city are now underwater. Marine surveys show portions of the harbour and coastal structures sit several metres below modern sea level. Scientists continue debating whether this resulted primarily from tectonic subsidence, earthquakes, rising sea levels, or a combination of all three. Sediment analysis suggests slow geological sinking may have occurred over centuries. If so, iotape provides rare evidence of how ancient cities gradually adapted to environmental collapse long before modern climate discussions existed. Some archaeologists believe entire sections of the harbour remain buried beneath underwater sediment. Sonar scans along sections of the coast hint at additional submerged structures still unexplored. Each new survey raises the possibility that critical parts of iotape's engineering systems remain hidden beneath the Mediterranean floor. What do you think explains the engineering precision and durability of iotape? Advanced ancient knowledge, lost techniques, or something else we still haven't uncovered? Share your thoughts in the comments below. Surrounded by the rugged landscape of southern Oman near Salalah, Ain Razat stood along one of the most important ancient frankincense trade corridors in Arabia. Archaeologists began closely studying the area during 20th century surveys of Dhofar's ancient water systems and caravan routes. What initially appeared to be a natural spring surrounded by ruins slowly revealed something far more unusual, evidence of a highly controlled hydraulic landscape operating in one of the harshest climates on Earth. Unlike massive monuments that dominate the horizon, Ain Razat hides its mystery inside engineering precision almost invisible to the naked eye. The greatest mystery surrounding Ain Razat is not the spring itself, but the sophisticated control of water flow around it. Dhofar receives seasonal monsoon moisture from the Indian Ocean during the Kharif season, yet for most of the year the surrounding environment remains semi-arid. Maintaining stable agriculture and caravan support systems in such conditions required extraordinary hydraulic understanding. Archaeological remains show carefully constructed channels, reservoirs, retaining walls, and distribution pathways positioned with remarkable accuracy across uneven limestone terrain. Even minor slope errors in ancient channels would have caused destructive erosion or stagnant water buildup. Modern hydraulic engineers know that maintaining efficient gravity-fed flow often requires gradients of less than 1%. At several ancient water systems across the ancient world, including Roman aqueducts, engineers maintained gradients averaging only a few centimetres per 100 metres. The famous Pont du Gard aqueduct in France, for example, drops roughly 17 metres across nearly 50 kilometres. What makes Ain Razat difficult to explain is that the local civilizations responsible for these systems left behind no obvious evidence of advanced surveying instruments comparable to Roman chorobates or later Islamic precision tools. Yet the channels appear deliberately calibrated to regulate seasonal flow fluctuations while minimizing water loss. Some researchers believe the builders may have used water level measuring methods, tensioned cords, astronomical orientation, or long-distance visual leveling techniques similar to those suspected in Persian Qanat engineering. However, no direct proof has ever been discovered. The engineering knowledge appears almost invisible, embedded directly into the landscape itself. Another major mystery involves the region's geology. Ain Razat sits within a limestone environment dominated by karst formations. Karst terrain is notoriously unstable for water storage because limestone naturally fractures, allowing water to disappear underground through cracks and subterranean channels. Yet several ancient reservoirs and collection areas near Ain Razat appear to have retained water far more efficiently than expected. This has led archaeologists to question whether ancient builders developed specialized waterproofing techniques now largely lost. In multiple ancient civilizations, advanced water sealing technologies existed far earlier than many historians once believed. Persian engineers created saruj, a waterproof mortar composed of clay, lime, ash, and organic materials. Roman concrete developed chemical reactions with seawater that allowed structures to survive for millennia. At Petra, the Nabateans engineered hidden cistern systems capable of storing enough water to support tens of thousands of people in desert conditions. Ain Razat may represent a southern Arabian version of this forgotten hydraulic science. Some excavation reports describe unusually compact sediment layers and artificial lining traces near portions of the ancient channels. If deliberate sealing methods were used here, it would suggest that the inhabitants understood hydrogeology at a surprisingly advanced practical level despite operating in a region often portrayed as technologically simple. One of the strangest aspects of Ain Razat is the environment itself. During the Kharif monsoon season, moisture from the Arabian Sea transforms Dhofar into one of the greenest parts of the Arabian Peninsula. Fog, mist, and low clouds dramatically reduce evaporation rates. Ancient structures at Ain Razat appear strategically positioned in areas with optimal humidity retention, cooler airflow, and reduced solar exposure. This has led some researchers to suspect that the site was intentionally designed to manipulate microclimate conditions. Modern environmental engineers use similar principles today. Temperature differentials, shade geometry, airflow corridors, and evaporative cooling systems are carefully calculated to preserve water and stabilize agriculture in dry climates. Some ancient societies achieved comparable effects without modern computation. Persian yakhchals preserved ice in deserts where summer temperatures exceeded 40 degrees Celsius. Nabatean architecture at Petra exploited canyon airflow to create cooler living environments. In Yemen, ancient terrace systems altered entire mountain ecosystems. At Ain Razat, the positioning of water channels and reservoirs may have created localized cooling zones capable of sustaining vegetation and caravan operations even during hotter months. If true, the site was not simply using nature, it was subtly engineering nature itself. The Dhofar region was once the center of the global frankincense trade, one of the most valuable industries of the ancient world. Frankincense resin was transported from southern Arabia to Egypt, Rome, Mesopotamia, Persia, India, and eventually China. In some Roman periods, frankincense rivaled precious metals in value due to its religious and medicinal importance. Ancient caravan networks crossing Arabia required carefully spaced water stations to survive. A single interruption in reliable water access could collapse entire trade routes. Ain Razat's hydraulic stability may explain why the site became strategically critical despite its isolated position. This raises a larger mystery. Was Ain Razat merely a local settlement surrounding a spring, or was it part of a much larger logistics network controlling trade movement across Arabia? Satellite mapping and archaeological surveys across Oman increasingly reveal interconnected caravan pathways, fortified stops, and water management systems extending across enormous distances. Some historians now believe ancient Arabian trade infrastructure was far more organized and technologically coordinated than previously assumed. The wealth generated through frankincense may have funded highly specialized engineering knowledge that disappeared after trade routes declined. If so, Ain Razat could represent only a surviving fragment of a much larger lost system. Perhaps the most difficult question is not how the system was built, but how it continued functioning for centuries. Ancient hydraulic systems require constant maintenance. Sediment accumulation, mineral deposits, biological growth, erosion, and seasonal flooding rapidly destroy unmanaged channels. Even modern concrete irrigation systems require continual repair. Yet archaeological evidence suggests water management around Ain Razat remained operational across multiple historical phases. This implies organised labour, technical oversight, and intergenerational transfer of engineering knowledge. Comparable systems elsewhere depended on highly specialised water experts. Persian Qanat networks required hereditary maintenance teams who understood underground tunnel behaviour. Roman aqueducts employed permanent engineering crews. In the Andes, Inca hydraulic terraces required constant coordinated upkeep, involving entire communities. At Ain Razat, no written manuals survive. No engineering diagrams remain. The knowledge system itself appears to have vanished almost completely, leaving behind only the physical evidence of its effectiveness. That disappearance creates one of the site's most unsettling mysteries. How much ancient technical knowledge has been entirely erased from history simply because it was transmitted orally rather than through durable records? Scattered around Ain Razat are foundations, stone alignments, and structural remnants whose exact functions remain uncertain. Some appear ceremonial. Others resemble storage platforms or hydraulic control features. Several orientations also seem deliberately aligned with terrain gradients and seasonal sunlight patterns. Water in ancient Arabia was not only a resource, it was deeply tied to political power and spiritual symbolism. Across the ancient Near East, springs often became sacred locations associated with divine protection, fertility, and survival. This creates another possibility. Ain Razat may have operated simultaneously as an engineering hub, caravan station, and ritual landscape. The blending of religion and hydraulic control was common throughout the ancient world. Egyptian temples controlled Nile irrigation cycles. Mesopotamian priesthoods regulated canal systems. Nabatean sacred spaces were integrated directly into water infrastructure. At Ain Razat, the separation between utility and spirituality may never have existed at all. Hidden within the limestone formations of the Swabian Jura in southern Germany, Hohle Fels Cave has emerged as one of the most extraordinary archaeological sites ever discovered, not simply for its age, stretching back over 40,000 years, but for the unsettling sophistication of the objects found within it. Excavations led by archaeologist Nicholas Conard from the University of Tübingen, particularly between the early 2000s and the 2010s, have revealed a dense concentration of artifacts attributed to the Aurignacian culture, often associated with some of the earliest modern humans in Europe. Among these discoveries are musical instruments, figurative sculptures, and personal ornaments, each pushing the boundaries of what researchers once believed possible for Ice Age societies. However, beyond the artistic and symbolic significance of these objects lies a deeper and more perplexing mystery, one centered on material science and engineering, the seemingly irrational yet highly effective technology used to process mammoth ivory. Mammoth ivory is not a forgiving material. Structurally, it is composed of dense dentin, with a complex internal pattern known as Schrieger lines, making it both extremely hard and highly susceptible to cracking under stress. Modern artisans working with ivory, even with precision tools, often face challenges in preventing fractures during cutting or carving. Yet, at Hohle Fels, artifacts dating back approximately 35,000 to 40,000 years display a level of craftsmanship that suggests not only familiarity with the material, but a mastery of it. And one of the most striking examples is the ivory flute discovered in 2009, reconstructed from multiple fragments and estimated to be around 35,000 years old. Unlike simpler bone flutes found in other regions, this instrument was not merely hollowed out. Instead, it was carefully split longitudinally, each half carved with remarkable precision, then reassembled to form a sealed acoustic chamber. The seams align so tightly that even under microscopic analysis, the join appears deliberate and controlled, raising immediate questions about the techniques used to achieve such precision without metal tools or adhesives as we understand them today. To put this into perspective, Kia experimental archaeology has attempted to replicate similar processes using only stone tools comparable to those available during the Aurignacian period. Results consistently show that while it is possible to carve ivory using flint blades, the process is slow, unpredictable, and prone to catastrophic cracking, especially when attempting to hollow out internal cavities or create thin walls. In contrast, the whole fells artifacts exhibit smooth internal surfaces and consistent wall thickness, indicating a level of control that exceeds what would be expected from purely trial and error methods. Some researchers have proposed that prehistoric craftsmen may have used controlled heating or soaking techniques to alter the mechanical properties of the ivory, softening it temporarily to reduce brittleness. However, there is currently no definitive archaeological evidence of such processes at the site. No specialized heating installations, no residue of binding agents, and no clear sequence of production stages have been identified, leaving a critical gap between the observed results and the presumed methods. This gap becomes even more pronounced when comparing Hohlerfels to other contemporary sites. In locations such as Geissenklusteler Cave and Vogelherd Cave, similar ivory artifacts have been found, including figurines and musical instruments, yet the density and apparent refinement of the Hohlfels assemblage stand out. The famous Venus of Hohlfels, dated to roughly 40,000 years ago, is carved from a single piece of mammoth ivory and features exaggerated anatomical forms with deeply incised contours. Achieving such depth and curvature without fracturing the material would require not only technical skill, but also an intimate understanding of stress distribution within the ivory, knowledge that, in modern contexts, is often informed by material science and engineering principles. The figurine surface also shows signs of smoothing and finishing, possibly through abrasion with fine-grained materials, suggesting a multi-stage production process that goes far beyond simple carving. Radiocarbon dating of the surrounding sediment layers places these artifacts firmly within a narrow time frame, indicating that this technological capability did not evolve gradually over tens of thousands of years at this site, but appeared relatively abruptly. This aligns with what some scholars describe as the Upper Paleolithic Revolution, or Creative Explosion, a period marked by a sudden proliferation of symbolic and technological innovations. Yet even within this broader context, the specific techniques observed at Hohlerfels remain anomalous. For example, while bone tools and simple carvings are widespread across Europe during this period, the complex manipulation of ivory, particularly the creation of composite structures like the flute, remains rare and geographically concentrated. Another layer of mystery lies in the apparent absence of corresponding tools. Excavations at Hohlerfels have yielded numerous stone implements, including blades and burins, but none that definitively account for the fine drilling and internal shaping required for the ivory artifacts. And microscopic wear analysis has identified some tools that may have been used for carving, yet the precision of the finished object suggests either the existence of specialized tools that have not been preserved or techniques that leave minimal trace. Organic tools made from wood or plant fibers could have played a role, but their complete disappearance over tens of thousands of years makes this hypothesis difficult to verify. Alternatively, it is possible that the artisans employed methods that maximized efficiency and minimized tool wear, achieving results that seem disproportionate to the apparent simplicity of their toolkit. Excavation campaigns throughout the 2000s and 2010s have continued to refine our understanding of the site, and with stratigraphic analysis confirming repeated human occupation and consistent production of high-quality artifacts. Despite these advances, the fundamental question remains unresolved. How did these early humans develop and transmit such specialized knowledge? The consistency observed across multiple artifacts suggests that this was not the work of isolated individuals, but part of a shared technological tradition, possibly passed down through generations. This implies the existence of teaching methods, apprenticeship systems, and perhaps even conceptual frameworks for understanding materials, elements typically associated with much later, more complex societies. When compared to later civilizations, such as those of ancient Egypt or Mesopotamia, where advanced material processing is well documented and supported by written records, the achievements at Hohlefels appear even more enigmatic. Those later cultures had access to metallurgy, organized labor, and accumulated knowledge over millennia. In contrast, the inhabitants of Hohlefels operated within a hunter-gatherer context, without agriculture, without permanent settlements, and without any known system of writing. Yet in at least one domain, the manipulation of a notoriously difficult material, they achieved results that challenge modern assumptions about the limitations of prehistoric technology. What do you think allowed humans over 40,000 years ago to process mammoth ivory with seemingly impossible precision? Was it a lost skill, or a form of knowledge we still don't fully understand? Where are you watching this video from, and what time of day is it for you? Share your location and time in the comments below. Northern Jordan, near the modern border with Syria and overlooking the Sea of Galilee, archaeologists uncovered an enormous underground necropolis beneath the ruins of ancient Gadara, today known as UnSolved. Initial excavations in the late 19th and early 20th centuries revealed hundreds of tomb chambers hidden beneath layers of collapsed basalt rock. What appeared at first to be a typical Greco-Roman cemetery soon became something far stranger. The deeper researchers explored, the more they realized this necropolis was carved not into soft limestone or sandstone, but into dense volcanic basalt, one of the hardest construction stones used in the ancient world. That single fact changed everything. Basalt is dramatically more difficult to cut than the sandstone of Petra or the limestone used around Rome. Modern geological measurements place basalt around 6 on the Mohs hardness scale, while many limestones range closer to 3 or 4. Even with modern steel tools, quarrying basalt remains slow and energy-intensive. Yet beneath UnSolved lies a maze of corridors, burial chambers, ventilation shafts, stairways, and vaulted ceilings, extending through massive black volcanic bedrock with surprising precision. For archaeologists, the necropolis created an uncomfortable question. How did an ancient civilization, working nearly 2,000 years ago, carve such an enormous underground complex into volcanic stone with tools that should have been far less effective? The mystery begins with the walls themselves. Many corridors inside the necropolis contain long parallel cutting marks unusually straight for hand chiseling. In several chambers, the surfaces appear almost machine-smoothed, with sharp geometric corners and consistent ceiling curvature. Roman and Hellenistic builders were undoubtedly skilled engineers, but the scale of labor implied here is staggering. Some estimates suggest that removing even a single cubic meter of basalt using traditional iron chisels could require dozens of man-hours. Yet the UnSolved network contains thousands of cubic meters of excavated stone. The engineering challenge becomes even more impressive when compared to other ancient underground sites. Roman catacombs near Rome were usually dug into soft volcanic tuff, a lightweight rock easy to carve. Cappadocia's underground cities in Turkey were excavated into soft ignimbrite. Petra's monuments were carved into relatively workable sandstone. UnSolved, by contrast, demanded excavation through dense basalt capable of dulling iron tools rapidly. Despite this, many chambers remain geometrically symmetrical, suggesting highly organized planning rather than gradual random digging. Even more mysterious is the necropolis ventilation system. Some burial chambers descend several levels underground, yet air circulation inside remains surprisingly stable. Archaeologists identified narrow shafts and side tunnels too small for human movement, but perfectly positioned to redirect airflow. Researchers suspect these acted as primitive pressure-balancing channels, creating natural ventilation through temperature differences between the surface and underground chambers. Similar passive airflow principles appear in Persian wind catchers and Cappadocian underground cities, but Umkais applied them inside volcanic rock with remarkable efficiency. The physics behind this is significant. Basalt absorbs and retains heat far longer than softer sedimentary stone. During the daytime, surface basalt heats intensely under the Jordanian sun, then slowly releases heat after sunset. By strategically placing narrow shafts between warm and cool zones, ancient builders may have created convection-driven airflow systems without mechanical assistance. Some modern engineers studying passive cooling architecture note that such thermal regulation principles resemble techniques used in contemporary sustainable building design. But airflow was only part of the puzzle. Humidity control inside the necropolis remains equally difficult to explain. Despite centuries underground, several burial chambers remained unexpectedly dry compared to neighboring archaeological sites in the Levant. Researchers found traces of mineral coatings and mortar mixtures containing volcanic ash and fine aggregates similar to Roman pozzolanic concrete. Roman marine concrete famously hardened over time through chemical reactions involving volcanic material, allowing harbours to survive for millennia. At Umkais, microscopic analysis suggests certain wall coatings may have functioned similarly, helping resist cracking and moisture penetration inside basalt chambers. What makes this unusual is geography. Jordan was not the centre of Roman volcanic concrete production. Most advanced pozzolanic formulas originated near Italian volcanic regions around Naples, yet Umkais appears to contain local adaptations of comparable technology. Some researchers believe engineers transported technical knowledge across the Eastern Roman Empire, while others argue the formulas were independently modified using regional volcanic materials. Either explanation implies a far more advanced exchange of engineering knowledge than traditionally assumed. Then there are the tomb alignments. Several chambers inside the necropolis appear oriented toward precise solar positions during seasonal transitions. During particular days of the year, sunlight entering narrow openings can briefly illuminate central sarcophagi deep underground. This phenomenon resembles solar alignments found at sites like Newgrange in Ireland or Abu Simbel in Egypt, where architecture interacted deliberately with celestial cycles. But accomplishing such precision underground inside basalt corridors required extraordinary geometric planning. Researchers still debate whether these alignments were symbolic, astronomical, or ritualistic. Ancient Gadara was a multicultural city influenced by Greek, Roman, Nabatean, and Semitic traditions. The necropolis may therefore represent a fusion of funerary beliefs combining astronomy, cosmology, and engineering. In many ancient societies, sunlight symbolized rebirth or passage into the afterlife. The fact that light penetrated certain Umkais chambers only briefly each year may not have been accidental. Ground-penetrating radar surveys added another layer to the mystery. Subsurface scans revealed multiple hidden voids beneath already excavated sections of the necropolis. Some cavities remain inaccessible due to collapse risks and unstable geology. Preliminary data suggests the underground complex could be significantly larger than currently mapped. If confirmed, Umkais may rival portions of Rome's catacombs in scale, while being carved through vastly harder stone. And that raises an even bigger question. Why construct such an enormous necropolis in basalt at all? From an engineering perspective, easier alternatives existed nearby. Softer stone formations would have reduced labour dramatically, yet the builders deliberately chose volcanic bedrock. Some archaeologists argue basalt symbolised permanence and endurance. Others suggest the elevated volcanic plateau offered structural stability and natural defence against erosion. But another possibility exists. Ancient engineers may have understood basalt's long-term resistance to humidity, collapse, and seismic damage better than modern historians realise. That theory becomes especially important in a region shaped by earthquakes. Kayes lies near the Jordan Rift Valley, part of the tectonic boundary associated with the Dead Sea Transform Fault System. Historical records document major earthquakes across the region for centuries. Many ancient cities nearby suffered catastrophic destruction, yet portions of the Kayes necropolis survived remarkably intact underground. Several chambers feature subtly curved vaulted ceilings, distributing pressure away from structural weak points, similar to anti-seismic load distribution used in later Roman engineering. In some tunnels, archaeologists observed intentionally narrow passage transitions between larger chambers. Modern structural engineers recognize that such bottleneck geometry can reduce stress propagation during seismic movement. Whether ancient builders understood earthquake mechanics scientifically or through accumulated experience remains unknown. But the survival of these underground spaces suggests they possessed far greater geological awareness than often assumed. Among the barren mountain valleys of Egypt's eastern desert, around 35 kilometers southeast of Aswan, archaeologists uncovered one of the most mysterious industrial sites of the ancient world. The area was first seriously documented during the late 19th and early 20th centuries after explorers discovered hundreds of inscriptions, ruined settlements, military outposts, and ancient mining tunnels scattered across the desert landscape. What initially appeared to be isolated ruins soon revealed something far more unusual. A massive industrial mining network operating nearly 4,000 years ago in one of the harshest environments on Earth. Temperatures in this region regularly exceed 45 degrees Celsius during summer. Annual rainfall is close to zero. Yet archaeologists uncovered evidence that large Egyptian expeditions repeatedly crossed this desert during the Middle Kingdom, particularly under rulers such as Senusret I, Senusret III, and Amenemhat III. More than 1,200 inscriptions have been identified at the site, many recording organised mining expeditions involving soldiers, officials, workers, stonecutters, scouts, and water carriers. The scale immediately raised a difficult question. How did a Bronze Age civilization sustain large industrial operations in terrain where survival itself is extremely difficult even today? The greatest mystery surrounding Wadi el-Hudi is not the amethyst itself, but the logistics required to obtain it. The mines are located far from the Nile River, meaning every drop of water, every food supply, every tool, and every worker had to travel through hundreds of kilometers of hostile desert terrain. Some inscriptions describe expeditions involving several hundred men. Even under conservative estimates, an expedition of 300 workers would require several tons of water per week merely to survive. Modern desert survival studies estimate that humans performing heavy labour in temperatures above 40 degrees Celsius may require 10 to 15 litres of water daily. This means Egyptian expeditions may have needed thousands of litres transported continuously across barren rock valleys with no stable wells nearby. What makes this harder to explain is the consistency of the operations. Wadi el-Hudi was not used once or twice. Archaeological evidence suggests repeated industrial activity across centuries. Defensive walls, storage buildings, guard posts, worker settlements, and road systems indicate long-term logistical planning rather than temporary exploration. Some researchers compare this organisational complexity to later Roman mining systems in Spain and Britain. Despite Wadi el-Hudi predating many Roman industrial operations by more than 1,500 years. Others argue that the Egyptians may have created hidden desert supply stations or seasonal water caches that remain undiscovered today. The amethyst veins at Wadi el-Hudi were embedded inside extremely hard metamorphic rock. Yet many ancient tunnels display narrow precision cuts and deep extraction chambers carved directly into the mountains. This creates a technological problem. During the Middle Kingdom, Egyptian miners supposedly relied primarily on copper chisels, dolerite hammerstones, wooden wedges, and fire-setting techniques. However, pure copper ranks only around 3 on the Mohs hardness scale, while quartz-based minerals approach hardness levels near 7. In simple terms, the stone being mined was significantly harder than the tools supposedly used to shape it. Similar engineering contradictions appear elsewhere in Egypt, especially at the granite quarries of Aswan and inside certain Old Kingdom stone structures. At Wadi el-Hudi, some tunnel walls contain extraction marks that appear unusually consistent, suggesting advanced control during cutting operations in confined underground spaces. Researchers believe miners may have combined thermal fracturing with repeated percussion methods to weaken the surrounding rock before extracting the amethyst. But even this does not fully explain the efficiency of the operation. Some tunnels penetrate deep into unstable rock zones with surprisingly organised layouts, indicating careful geological understanding rather than random digging. One of the strangest aspects of Wadi el-Hudi is the apparent geological accuracy of the mining expeditions. Ancient miners repeatedly located productive amethyst veins hidden within remote mountain systems across the eastern desert. Even with modern surveying technology, locating mineral veins in desert mountain environments remains difficult and expensive. Yet Egyptian expeditions consistently identified profitable extraction zones long before modern geology existed as a science. Some archaeologists believe generations of accumulated observational knowledge allowed miners to recognize subtle surface indicators such as rock coloration, fracture patterns, or mineral traces. Others suggest the Egyptians developed surprisingly sophisticated practical geology through centuries of experimentation. The accuracy becomes even more remarkable when compared with many medieval mining operations, which often relied heavily on luck and shallow excavation. At Wadi el-Hudi, Egyptian miners repeatedly targeted productive areas with unusual precision. The eastern desert is one of the easiest places on Earth to become lost. Large areas contain nearly identical rocky valleys, dry riverbeds, and barren mountain ridges extending for hundreds of kilometers. Yet ancient expeditions repeatedly traveled between the Nile Valley and Wadi el-Hudi with remarkable consistency. Archaeologists have identified ancient pathways, guard stations, and travel routes connecting the mines to the Nile trade network. Without compasses, modern maps, satellites, or GPS, Egyptian desert travelers somehow maintained accurate navigation across terrain, where even experienced modern hikers can lose orientation quickly. Some historians believe they relied on solar positioning, stars, mountain silhouettes, and memorized route systems passed between expedition leaders. But the efficiency of the surviving road network suggests something more systematic. Certain routes appear optimized to reduce exposure to heat while maximizing access to defensible terrain and possible water sources. This implies advanced environmental knowledge accumulated through long-term desert exploration. Another mystery involves the militarized nature of the site. Wadi el-Hudi was not merely a mine, it functioned almost like a fortified industrial colony. Archaeologists discovered defensive walls, watchtowers, narrow entry checkpoints, and strategically positioned guard posts overlooking mountain passes. Some forts were built at elevated positions capable of monitoring approaching travelers from long distances. This level of military infrastructure suggests the Egyptians considered the amethyst mines strategically important. Inscriptions reference desert raiders and hostile nomadic groups capable of attacking mining expeditions. Protecting the mines therefore required constant military oversight. What surprises researchers is how effectively the defences use natural terrain. Many structures were positioned to exploit narrow canyon entrances and elevated sightlines, resembling military principles later seen in Roman frontier forts and medieval mountain fortifications. Modern audiences often underestimate the importance of amethyst in ancient Egypt. During the Middle Kingdom, high-quality purple stone was associated with royalty, elite jewellery, religious symbolism, and political power. Before large amethyst deposits were discovered elsewhere in later centuries, Egyptian amethyst was considered extremely rare. Some historians compare its prestige value to lapis lazuli in Mesopotamia or jade in ancient China. The willingness to risk large expeditions through lethal desert conditions suggests the stone carried enormous economic and symbolic importance. Certain royal ornaments, scarabs, necklaces, and ceremonial objects used amethyst imported directly from Wadi el-Hudi. Yet despite the immense investment, historians still debate whether the true value of the site was purely decorative. Some theories propose that control of luxury resources played a critical role in maintaining royal legitimacy and elite political networks across Egypt. One overlooked mystery is the durability of the site itself. Desert environments create intense thermal stress. Rock and mud brick structures experience rapid expansion during daytime heat and contraction during freezing desert nights. Over centuries, these thermal cycles normally destroy ancient buildings. Yet many walls, pathways, and structural remains at Wadi el-Hudi survived for nearly 4,000 years. This suggests Egyptian builders understood how to construct architecture adapted specifically for desert geology and temperature variation. Certain walls appear positioned to minimize erosion from flash floods moving through seasonal wadis, while settlement layouts reduced direct exposure to prevailing desert winds. Even today, engineers designing structures in arid climates must carefully calculate thermal expansion and material fatigue. The survival of these ancient installations suggests a practical environmental engineering knowledge far beyond what is often associated with Bronze Age societies. Do you think the people of ancient Egypt possessed engineering knowledge far more advanced than history officially admits? Share your thoughts and theories in the comments below. Far above the waters of Lake Nasser in southern Egypt, a lone rocky fortress still rises where entire ancient cities vanished beneath the floodwaters. Qasr Ibrim was discovered by modern archaeologists long before the construction of the Aswan High Dam, but after the dam was completed in the 1960s, the site became something even stranger, an isolated archaeological island surrounded by water and desert. Located roughly 235 kilometers south of Aswan near the old Nubian frontier, Qasr Ibrim survived while dozens of neighbouring temples disappeared underwater forever. That survival turned it into one of the most important time capsules in African archaeology. Unlike most ancient cities that belong to one civilization, Qasr Ibrim contains nearly 3,000 years of continuous occupation. Egyptians, Kushites, Romans, Byzantines, and Islamic kingdoms all used the fortress without fully destroying the earlier structures. Instead, they built directly on top of older walls, chambers, and foundations. Archaeologists describe the site as a vertical historical stack where entire civilizations overlap physically. Some sections contain as many as 6 different construction phases compressed into a single wall system. This layered architecture has made excavation extremely difficult, because removing one layer risks damaging another civilization beneath it. One of the greatest mysteries surrounding Casa Ibrim is its unusual structural durability. The fortress was built mainly from Nubian sandstone and mud brick, materials that normally erode rapidly under severe desert temperature fluctuations. In this region, daytime temperatures can exceed 45 degrees Celsius, while nighttime temperatures drop dramatically, causing stone expansion and contraction that slowly fractures buildings. Yet many walls at Casa Ibrim remained standing for over 1,000 years even after humidity increased following the creation of Lake Nasser. Some researchers believe ancient Nubian builders used mineral-rich Nile mud mixed with salt compounds and organic binders to create a primitive thermal-resistant mortar. Laboratory analysis detected unusually high concentrations of calcium salts and fine clay particles that may have reduced cracking. Modern experiments attempting to replicate these mixtures have produced inconsistent results, suggesting the original formula may have depended on extremely precise local materials. The mystery becomes even deeper when compared to other desert fortresses. Many Roman frontier forts in North Africa collapsed after centuries of thermal erosion, while sections of Casa Ibrim remained structurally stable despite older foundations. Some engineers compared the fortress's layered wall behavior to modern composite construction, where different material densities distribute stress more evenly across the structure. No evidence suggests the Nubians possessed advanced machinery, yet the long-term performance of the walls continues to surprise preservation experts today. Another unexplained feature is the fortress's passive cooling system. Excavations revealed underground grain storage chambers, connected by extremely narrow ventilation shafts. These shafts created controlled airflow capable of lowering interior temperatures naturally. Tests performed inside reconstructed chambers showed temperature reductions of several degrees compared to the external desert air. Some rooms also maintained remarkably stable humidity levels despite the harsh environment outside. The engineering principles resemble modern passive cooling architecture used in Middle Eastern wind towers and underground thermal storage systems. What makes this even more remarkable is the scale of food preservation. Archaeologists discovered preserved wheat, barley, dates, and seeds that survived for centuries. Organic preservation at Nile sites is normally poor because humidity and microbial activity destroy food remains quickly. At Casa Ibrim, however, the fortress itself may have created a unique microclimate. The high elevation, enclosed chambers, dry desert airflow, and thick walls combine to produce natural preservation conditions similar to controlled storage facilities. Some scholars describe the site as an accidental ancient climate-controlled archive. That archive produced one of the most important discoveries in Nubian history: thousands of surviving manuscripts. Casa Ibrim preserved documents written on parchment, papyrus, leather, wood, and textiles in languages including Egyptian, Greek, Coptic, Arabic, Old Nubian, and Meroitic-related scripts. Few sites in Africa contain such a continuous written record across so many civilizations. Some Old Nubian texts remain only partially translated today because the language itself is still incompletely understood. These documents transformed modern understanding of medieval Nubia, proving the region possessed sophisticated administration, trade systems, taxation records, and religious scholarship long after many historians assumed Nubian civilization had declined. But even the manuscripts raise strange questions. Why were they preserved so effectively here, while nearby settlements lost nearly everything organic? Some researchers suspect the fortress's internal airflow and rock insulation created a stable dry environment almost identical to modern archival preservation standards. Others believe certain storage chambers may have been intentionally engineered for long-term document protection. If true, That would suggest Nubian administrators understood preservation principles far more advanced than previously believed. The military design of Qasr Ibrim is equally mysterious. The fortress sits on steep cliffs overlooking one of the narrowest strategic corridors along the Nile. Approaching armies would have been forced through highly visible routes exposed to defenders above. Yet the internal defensive system is what confuses military historians most. Narrow corridors, restricted entry points, elevated kill zones, and overlapping wall positions resemble defensive concepts found in medieval castles built centuries later in Europe and the Middle East. Some passageways intentionally force attackers to turn sharply while climbing upward, exposing their unshielded sides to defenders. Similar strategies later appeared in Crusader fortifications such as Crac des Chevaliers, but parts of Qasr Ibrim may predate them by hundreds of years. The site also reveals evidence of advanced water management despite its isolated desert location. Maintaining a permanent population on a rocky outcrop surrounded by arid terrain should have been extremely difficult. Archaeologists uncovered cistern systems, drainage channels, and storage basins capable of collecting and preserving water efficiently. Some theories suggest the builders exploited seasonal Nile flooding combined with underground seepage and nighttime condensation. Modern researchers studying atmospheric water harvesting noted that certain stone surfaces at the fortress may have enhanced condensation during cooler desert nights, potentially increasing moisture collection naturally. Religious transformation inside Qasr Ibrim adds another layer to the mystery. Ancient Egyptian temples were later converted into Christian churches, and some of those churches were eventually transformed into Islamic structures. Yet instead of demolishing earlier architecture completely, many civilizations preserved large sections of older walls and foundations. This unusual continuity suggests later builders recognized the structural superiority of existing engineering rather than replacing it entirely. In some chambers, Christian paintings survive beside reused pharaonic stone blocks inscribed thousands of years earlier. Compared with famous archaeological sites like Petra, Masada or Machu Picchu, Qasr Ibrim remains relatively unknown to the public. Yet scientifically, it may be even more valuable because of its uninterrupted occupation history and exceptional preservation conditions. Petra lost most organic material. Masada preserves mainly Roman period remains. Machu Picchu existed for only a relatively short period. Qasr Ibrim, however, records nearly 3 millennia of continuous adaptation to climate, war, political collapse, and changing religions. Perched above the windswept coastline of southern Africa, Blombos Cave has quietly forced archaeologists to confront a deeply unsettling possibility. That complex technological thinking, once believed to belong to relatively recent civilizations, may have emerged tens of thousands of years earlier than expected, only to vanish and reappear much later in human history. Discovered in the early 1990s, and extensively excavated beginning in 1991 under the direction of archaeologist Christopher Henshelwood, the cave has yielded a series of findings dated between approximately 70,000 and 100,000 years ago, pushing the boundaries of what is considered possible for early Homo sapiens. Among its most astonishing discoveries are engraved ochre fragments bearing deliberate geometric patterns, and carefully perforated shell beads likely used as personal ornaments, and, most controversially, what appears to be a fully developed ochre processing workshop, a system so methodical that many researchers now describe it as one of the earliest known examples of chemical technology. At the center of this mystery lies a set of artifacts uncovered in layers dated to roughly 100,000 years ago. 2 abalone shells used as containers, each containing a reddish compound composed of finely ground ochre mixed with crushed bone, charcoal, and a liquid medium believed to be animal fat or marrow. Accompanying these were hammerstones, grindstones, and bone tools stained with pigment, suggesting not a random accumulation of materials but a deliberate multi-step production process. What makes this discovery extraordinary is not merely the presence of pigment. After all, ochre use has been documented in other Middle Stone Age sites, but the clear evidence of systematic preparation. The ochre was not simply collected and applied, it was processed, combined with other substances, and stored for later use. This implies a level of planning, material knowledge, and procedural consistency that resembles a primitive form of chemical engineering. To understand how unusual this is, it is essential to compare Blombus Cave with other known archaeological contexts. In many early human sites, ochre appears as isolated fragments, often showing signs of scraping or grinding, suggesting its use as a colouring agent or symbolic material. However, these instances rarely demonstrate the full chaîne opératoire, the complete operational sequence, from raw material acquisition to final product storage. At Blombos, by contrast, researchers identified a coherent toolkit and spatial organisation that together indicate a structured production system. The presence of abalone shells as mixing vessels is particularly significant. These shells, with their natural concave shape and durability, functioned effectively as containers, allowing for the mixing and preservation of the pigment mixture. This is not an improvised solution. It reflects an understanding of material properties and functional design. Even more striking is the composition of the pigment itself. Experimental archaeology has shown that combining ochre with fat or marrow creates a more stable and adhesive substance, is suitable for application to skin, objects, or possibly cave surfaces. The addition of crushed bone may have altered the texture or consistency, while charcoal could have influenced the colour or chemical behaviour of the mixture. Such combinations suggest that the inhabitants of Blombos Cave were not merely using natural resources, but actively modifying them to achieve desired outcomes. This is a hallmark of technological behaviour, one that requires not only manual skill, but also cognitive abilities such as foresight, experimentation, and the transmission of knowledge across individuals or generations. When placed within a broader timeline, the implications become even more profound. Comparable evidence of pigment processing and storage does not appear again in the archaeological record until much later periods, and particularly during the Upper Paleolithic, around 40,000 years ago, when cave art flourished in Europe. Even then, while pigment preparation is evident, the level of organisation seen at Blombos remains exceptional. If we look further ahead to ancient civilizations such as Egypt, around 3,000 years before the Common Era, we find highly sophisticated pigment technologies, including the production of Egyptian blue, a synthetic pigment requiring controlled heating and precise chemical ratios. Yet the gap between Blombos and these later developments spans tens of thousands of years, raising a critical question. Why does such an advanced system appear so early? And why is there so little evidence of its continuous development? Excavations conducted between 1991 and 2011 have reinforced the interpretation of Blombos as a site of repeated, organised activity, rather than a one-time occupation. Stratigraphic analysis reveals multiple occupation layers, each containing variations of similar tools and materials, suggesting that the pigment production process was not an isolated experiment, but a recurring practice. Radiometric dating techniques, including optically stimulated luminescence, have consistently placed these activities within the same general time frame, lending credibility to the notion that this technological behaviour persisted over generations. Furthermore, microscopic analysis of the tools has identified where patterns consistent with grinding and mixing, while residue analysis confirms the presence of ochre-based compounds. Despite this wealth of evidence, significant questions remain unresolved. One of the most puzzling aspects is the purpose of the pigment. While it is often assumed that ochre was used for symbolic or decorative purposes, such as body painting or ritual marking, there is no direct evidence linking the Blombos mixture to specific applications. Could it have been used as an adhesive, perhaps in tool making or hafting? Some researchers have proposed this possibility, noting that ochre-based compounds can enhance the binding properties of natural glues. However, the exact formulation found at Blombos does not perfectly match known adhesive recipes, leaving the question open. Alternatively, the pigment may have served multiple functions, indeed combining practical and symbolic roles in ways that are difficult to disentangle. Another unresolved issue concerns the origin of the knowledge required to produce such mixtures. The process involves several steps: selecting appropriate raw materials, grinding them to the correct consistency, combining them in specific proportions, and storing the result in suitable containers. Each of these steps requires not only individual skill, but also an understanding of cause and effect, knowledge that must have been acquired through repeated experimentation or passed down through social learning. Yet the archaeological record offers little insight into how this knowledge was developed or transmitted. There are no written records, no direct evidence of teaching, and no clear evolutionary pathway leading to this level of sophistication. This has led some scholars to propose that Blombos represents a localized innovation hotspot, where unique environmental or social conditions allowed for a temporary leap in technological complexity. The comparison with other Middle Stone Age sites further highlights the uniqueness of Blombos. Sites such as Pinnacle Point, also in South Africa, show evidence of early ochre use and heat treatment of stone tools, indicating advanced cognitive behavior. However, even in these contexts, the kind of integrated multi-component production system seen at Blombos is rare. In Europe and Asia, similar developments appear much later, often associated with the spread of modern humans and the emergence of symbolic culture. This raises the possibility that the behaviors observed at Blombos were not widely shared or did not persist long enough to influence broader human populations. What do you think? Was the paint workshop at Blombos Cave a forgotten breakthrough, or evidence of an ancient knowledge system we still don't fully understand? Share your thoughts in the comments below,